Today we're going to continue the morning presentations with a session on how Antarctica and the Southern Ocean affect global climate and ocean circulation, and another session on Southern high latitude biota and ecosystems, and a final session on how a shifting ice sheet might affect sedimentation and biogeochemical cycles. In the afternoon, we're going to have two breakout sessions. The first is a repeat of yesterday's format, where the discussions will be session specific and focused on identifying science priorities and capabilities, and a final interdisciplinary breakout room that will be more free-flowing discussion about the differences and commonalities between necessary capabilities that each session has identified. And we might have a couple of tweaks to that, so stand by. We're now going to begin with session 4. Ted Maxim will be moderating the session, and if all presenters for session 4 could please come sit on stage, that would be great. So with that, I'll hand it over to Ted.
Yeah, and then you can.
Okay. All right, thank you, Paula. So our first speaker for this session, this session is focused on the interaction between Antarctica and the Southern Ocean and global climate and ocean circulation. Our first speaker for this session is Sarah Perkey. Sarah is an assistant professor at Scripps Institution of Oceanography at UC San Diego.
Got it. Okay, thanks. Push forward. Oh, coming. Okay, perfect. Okay. Well, first I can start by thanking the organizers for having me today. And today I get to introduce the section here talking about Antarctica and the Southern Ocean and the effects it has on global climate and ocean circulation. Maybe. Oh, there it goes. Okay, so to start off, when we're thinking about the role that the Southern Ocean plays, we have to start with this introductory slide, looking at the meridional overturning circulation. I like this one by Talley et al. From 2013 that really puts Antarctica in the center, because Antarctica and the Southern Ocean play a really key role in the north to south transport of heat and other ocean properties throughout the global ocean. And it's really important to note that most of the global ocean below 1,000 meters is going to be ventilated in the Southern Ocean. And it really plays a key role in the overall ability for the atmosphere and ocean to communicate with each other. So in this figure, it has Antarctica in the middle, and it shows some of the key pathways that Antarctica is able to get water from the surface, communication with the atmosphere, and then back into the deep ocean. And really a key point from this talk is to think about how the Southern Ocean and Antarctica mediates the strength of this meridional overturning circulation. And to do that, I want to focus on two key regions. One is on the continental shelf, and looking at the interaction between the ocean, ice, bathymetry, and atmosphere. And the second one is within the ACC, looking at the role that the overturning circulation plays in this larger formation of intermediate waters in the upwelling of deep waters. So going to the Antarctic shelf, we've seen versions of this figure before, but I want to point out some key features. So first, this region is extremely key to climate because of reasons that we've already heard, which is it can control the rate that we get this warm deep water, which is shown in red there, up onto the shelf and close to the glaciers, and therefore accelerating or decelerating the rate of melting that we see of the glacial ice. But in addition to that, it plays a key role in setting the quantity of sea ice and the export rates. And it also plays a really key role in setting the rate of deep water formation. And so in this figure, we see that here, and I also want to point out that this is a very kind of dynamic, it's a very complicated, and it's a very coupled system where we have to think about the wind forcing. We have to think about the sea ice production and transport, which is a non-trivial question that I think is still a very active area of research. We have to think about the slope exchange, which again is a complicated system where we have to think about many different timescales, all the way down to the tidal timescales and mixing processes. And then we have to think about the ocean ice interaction at the front, which is also kind of emerging physics that we're trying to understand. And then just to point out, we have talked a little bit about slides are slow. Advance, I guess there's some animation, sorry about that. When we think about, again, going back to the Antarctic bottom water formation, this water that is being exported is the largest volume-wise of water being produced in the global ocean. And this is just a figure by Johnson et al. Showing the spatial extent, here showing depth range that water primarily fills. So throughout most of the ocean, it's going to be kind of 2,000 to 4,000 meters. And really the data challenges here is that it's a very coupled system. It's a harsh environment, and the dynamics are very complicated. And the second region that I wanted to kind of introduce is looking at the dynamics across the ACC. So in the Southern Ocean, we have one of the strongest currents in the world that goes all the way around the continent. And here, the dynamics are primarily driven by the wind-driven circulation. And so what that's shown is these yellow arrows on the top, and then I've put some dots on above showing the meridional variation in the wind strength. And so a little physical oceanography 101, because I know we're an interdisciplinary group. But here what matters is actually the variation going from the strongest wind source in the middle. As we move north, it gets a little bit less. And because of the Coriolis force, that's going to end up in water converging and downwelling. Into the south, we're going to have a decrease in the wind strength, which is going to allow for really strong Ekman upwelling. And that is what really allows this pathway of carbon coming from the deep ocean going to the surface. And then also the formation of the intermediate waters to the north, which allows us to sequester anthropogenic heat into the deep ocean. And kind of the data challenges here is that it's somewhat remote in the Southern Ocean, and again, really large and small spatial scales matter. So I think in the last decade, it's become increasingly clear that even on the submesoscale plays a really key role in studying the strength of this overturning circulation. So now moving into observations and kind of what I think we need moving forward. So I divided this into two categories. The first one, thinking about what we need to monitor the Southern Ocean heat and carbon. And really the scientific question here is, what is the net ocean heat uptake in carbon sink that's coming from the Southern Ocean? And to do this, what we really need is climate quality data, which means we really care about the highest accuracy. We need sustained observations because this is a decadal signal. And to do this, we're going to need a combination of autonomous and high quality ship-based observations. And so what's shown on the right is the observational network that we primarily use right now to monitor ocean heat and carbon uptake, which is a combination of Argo floats and the ghost ship repeat hydrography, which is in lines. And for the most part, I think we have a pretty good start on this system. We just need to continue and expand it into the future. And so what's shown here and what the last 2 decades of Argo data has shown us is that the Southern Ocean plays a very key role in both of these processes. So on the top is showing the global trend in ocean heat content from Argo. And then on the right is showing the zonal mean. And what we can see is that these 2 key regions, kind of south of 30, play a substantial role in the net uptake of heat that the ocean is able to take up. And so again, just to remind everybody, the oceans take up over 90% of the net anthropogenic warming that we've seen. And so when we talk about global warming, we're actually talking about ocean warming, and that ocean warming is going into the Southern Ocean. And so in terms of global climate, we really need to be able to monitor this signal, how much heat is going south of 30 degrees south into the ocean. And then when we look at the deep ocean, again, going back to the Antarctic bottom water, at the moment, over the past couple of decades, we're mainly monitoring that from ship-based hydrography. And that is the figure that you see on the left. And so while it's smaller than the surface ocean, still a fair amount of heat is going into the Southern Ocean due to changes that we're seeing around the Southern Ocean. And just to point out that while the last couple of decades we've looked at repeat hydrography, the figure on the right is from Johnson et al. 2019, and he was using deep Argo data in the Brazil basin to start to monitor changes from autonomous platforms. And just to remind myself, this is a picture of a CTD to kind of point out that this program, Deep Argo, is not independent of ships quite yet. We still need it. And then finally, last but not least, I've been showing trends, but to kind of understand the dynamics here, we really need to know the year-to-year variability. So this is showing what we can do with Argo-based products is actually look at the year-to-year variability in ocean heat content. And then moving on to carbon, recently we have started putting autonomous pH sensors on floats, and this is results from the SOCOM array, which is showing both ship-based estimates of carbon fluxes in the background, and then the float data as those small red circles. And what's being shown here is, first of all, there's a huge gradient from south to north of carbon flux from the ocean to the atmosphere. And all those upwelling regions, it's going to control the amount of old water that's reaching the surface, allowing for carbon outgassing. And then north is going to be where you're having those waters being formed, and it's allowing for the subduction of water and the uptake of anthropogenic heat or anthropogenic carbon. And it's just important to point out that the background signal here is huge. And so when we're talking about the anthropogenic signal, it's a really small deviation of the background circulation that we still need to understand better. And also the difference between the left and the right is the summer and the winter. And it points out that the winter processes here are very key. And at the moment, it's still very difficult to get ships into the ice zone in the winter. And again, just to point out, while I am focusing a little bit on autonomous measurements here, these, especially the ocean chemistry, is not decoupled from ship-based observations. In order to make these estimates from the floats, we're only measuring one of the carbon parameters. We need to estimate at least one of the other ones, and these are coming from empirical relationships that we're still finding from ship-based data. So it's very key that we get into the ice zone during winter. And so last, looking at what I did talk about is what I think we're doing well and that we need to continue into the future, which is monitoring ocean heat and carbon. I think the real questions and where we're going in the future is to understand the mechanisms that are controlling the MOC in this rate flux. In here, going back to these pictures, it's talking about what are the levers here, what allows this to be stronger or weaker, and how do each of these parts of the system kind of play into that. And so the questions here are fundamentally, what are the variabilities of the circulation? And here, circulation means this meridional returning circulation, the strength of the AC, and the strength of the various fronts and currents around Antarctica that we need to understand. And we need this to really understand what the heat fluxes are onto the shelf and its variability, and think about the variability in the deep water formation, and think about the freshwater budget. And here, really the challenges being the fact that it really does span very large scales, it's seasonal dependent, and it's extreme environment, and it's a very coupled system. And so my last slide here is just thinking about what I think we need in the future. And so yesterday we heard a lot about kind of the needs of the shelf and adjacent regions. And it is a key region, obviously, and we heard over and over again that we need to get under the ice, and we need to get under the ice in the winter, so that's not new. I do want to think about or present to this group to think about the fact that it is really a coupled system. And so when we're designing our observational network, we need to be able to resolve all of the pieces together. And so in the exercise yesterday, for example, we're thinking about prioritizing what we need to observe, but it is key that kind of all of those pieces come together and that we understand that we're not going to get the ocean heat flux correctly without understanding the front slope structure or the dynamics under the shelf and the bathymetry and the sea ice and the wind. And so we should think about that when designing our observational network. I also put hydrography on here because we didn't hear that much about hydrography. There's still a lot of things that we need to look at from ship-based observations, ocean tracers being one of them. So the figure on the right is some recent work looking at CFC data, which is telling us kind of how water is ventilated throughout the global ocean. And using this, we can also kind of look at the changes in circulation. We need to extend Argo. So the figure on the bottom is just showing some work we did with the deep Argo under ice in the winter, showing kind of the evolution and how the Antarctic bottom water is moving. And what we're going to hear about here through the panelists is kind of what we need to do looking at past climates to inform us about our current climate. And just making a plug that when we're thinking about the observations, we also think about the modeling community and how it's going to help us answer these questions.
All right, thank you, Sarah. We have 3 minutes for questions, which we'll read out from Slido.
First question, what observations can not be completed using autonomous systems and must be done from ship-based surveys? In the future, would it be possible that all key measurements in this vein could be done with autonomous platforms?
That is a great question. So I try to touch on that a little bit. I think first off, no, I don't see a future where autonomous vehicles are going to ever be decoupled from ships and that we're not going to need that ship grounding truth, even for the things that we can measure. And I say that from this climate perspective. I think as climate scientists, when we're looking at things like ocean heat uptake and carbon, we nowadays have the world looking at us. These need to be very precise. We need redundancies in the system. And we need climate quality. So I work in the sensor community. The sensors are getting better every day, but there are always problems with them. They drift, and you are always going to need that grounding truth that's going to come from people on ship taking the measurements. And then finally, I think there are a lot of things that we don't measure that are going to be very, very challenging to measure autonomously. Tracers, isotopes, we're talking about glacier melt. You need to look at different variations in the isotopes can tell you about stuff like that. Again, with the carbon system, until we have a really functioning alkalinity sensor, we're going to definitely need to continue to get that carbon budget from a combination of autonomous and ship-based.
Thank you. Next question. How to promote the role of advanced technologies against ocean acidification and eutrophication and increase the key role of science and technology innovations?
I mean, I think that there is investment, just like we are investing in our ships because of how the questions that we're looking at in the future, we need to be investing both in autonomous sensors and in ships simultaneously. So the technology is coming along, but it's coming along through the community investing a lot of time in development work and working closely with engineers and actually other disciplines across the board who are also trying to measure similar things in other regimes.
Great, thank you. That was the last question we had on Slido.
Great, thanks.
All right, so we're going to do a series of flash talks, 5-minute flash talks. Our first flash talk is going to be given by Ed Brooke. Ed is a university distinguished professor in the College of Earth, Ocean, and Atmospheric Science at Oregon State University.
Okay, hi everybody. Can let me know if you can't hear me.
I think you're muted still.
Not muted on my end. I think you can hear me now.
Yes.
Yes.
Okay, thank you. Yeah, I'm Ed Brooke. I'm a professor in Earth, Ocean, Atmospheric Sciences at OSU. I'm also the director of a new entity. It's an NSF Science and Technology Center called the Center for Oldest Ice Exploration, which is attempting to extend the length of the ice core record. One of the two emissaries from the ice core community at this meeting. You heard from Peter Neff yesterday. So I'm not going to talk today about work that we would do directly using a ship, but I would like to talk about the intersection of deep ice coring research and what's happening in the near future with paleoceanography in the Southern Ocean. The context here is what we call the deep ice core records, not necessarily a well-defined term, but referring to data that go back through the last glacial maximum, and in many cases much further. And there are a number of such cores. Most of them are shown on the map that you see on the left-hand side. And ice cores are important in this context because they are sitting on the continent receiving information that's influenced by things that happen in the Southern Ocean, of course. And they have certain advantages, very high accumulation rates, very accurate chronologies, but of course have the disadvantage of being far south on the continent and certainly not seeing everything. Of course, another chief advantage of the ice core record is it tells us about the greenhouse gas history, which is a lot of what I'll be talking about here. There are two sort of big directions in the ice core community right now, and I'll talk a little bit about both of those for this context. One of them is trying to understand the history of waste collapse during the last interglacial period, with the idea that that'll tell us something about the sensitivity of waste to future warming. There are a number of projects that are directed towards that problem. One is on this map here, Skytrain Ice Rise, recently completed by the British Antarctic Survey. Another planned by the United States is where that red dot is, which is the Hercules Dome project, hopefully drilled in the near future. The idea is to sort of look in the regions around waste to see if there's evidence for waste collapse. But of course, if it did collapse, we're not going to drill into ice that's there. And so we're going to see sort of an indirect record of what was happening, and clearly understanding the history of waste from the ocean is a very, very central problem for climate science. The other direction that the ice core community is going now is trying to extend the record beyond the 800,000 year limit of the Dome C ice core, the European project at Dome C. And see if my animation arrows work here. Yeah. Okay, so the existing continuous ice core record goes back 800,000 years through most of the 100K world. But there's intense interest in extending this further to get back through the mid-Pleistocene transition and into the 40K world to understand what Antarctica was doing during that time period. And there are several international efforts directed at trying to find a place in Antarctica that can go back in that far. I think we'll get there. Coldex, the center I'm directing, is one of those efforts. And there is another important project in Europe and in Australia going forward in that direction. So we're going to be quite interested in paleoceanographic records that cover that time period. And then we're also finding older ice. In fact, we have ice that back to about 4 million years trapped in the mountain ranges in a place called Allen Hills in Antarctica, and we're exploring other places like that. That won't be continuous, but we're getting snapshots of climate that go back that far. And so understanding the Southern Ocean and those time scales will certainly bring connections to that world. I'd like to go to the next slide if I can. I'm having trouble advancing. Okay, so I only have a minute or so left. I approached the question here with a table to try to squeeze a lot of information in. And basically, ice cores are telling us a lot of things about biogeochemistry, climate, and glaciology, the types of things that Sarah talked about in the modern world, telling us about the greenhouse gas history, telling us about changes in biogeochemistry of iron, for example, that might influence ocean productivity, telling us maybe about changes in sea ice through tracers like sodium in the ice. But we need to understand the ocean context for all of these records because we're only seeing part of the system, obviously. And so it really getting a four-dimensional picture of the Southern Ocean biogeochemistry is key. Getting a complete picture of the history of the carbon budget around the Southern Ocean is key. Ice cores are also telling us a lot about climate and glaciology on the continent and off the continent. We now have records of mean ocean temperature from noble gas ratios in trapped air, which gets the things Sarah was talking about ocean heat content. We have very good data now about variability in temperature and accumulation across the ice sheet on around 100,000 year timescale, which leads to questions about moisture transport, what controls stable isotopes in the atmosphere, what controls the linkages between climate at high latitudes and the rest of the climate system. We can see things about ice dynamics from ice cores. Peter Neff talked about this. We need to understand how what we see it on the land is interacting with what's happening in the ocean. And then just to circle back to what I was talking about earlier, we really hope that we can extend the detailed ice core record back in time, and getting a full picture of what's happening needs. We also need to get detailed sediment records that go back over that time period. Okay, I'll stop there. Hopefully I didn't go over too long.
All right, thank you, Ed. So we're going to save our questions for the end of the flash talks. Our next talk is by Alexander Haumann. Alex is a research group leader at the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research in Germany.
Just a reminder, while we're
Hi.
getting Alexander's slides up, please use Slido to put questions in.
All right, I hope you can hear me all fine. Hi, everyone. Thanks, Ted, for the introduction. So I was tasked with, somehow my slides are moving. Not sure what is happening. So I was tasked with how does the Southern Ocean mediate fluxes of heat, carbon between the continent, the ocean, and the atmosphere? And the answer to this question might actually be quite simple, that you say it's through the ocean circulation and mixing that the Southern Ocean plays such a crucial role. And this is mainly because in the Southern Ocean, it's estimated that roughly about 80% of all deep waters return to the surface, and then they're circulated around the continent. And while doing this, they actually release CO2 and heat to the atmosphere in the first instance. And then as you go further north and these waters are modified, they take up anthropogenic heat and carbon, and it's estimated that it's about 13% of all anthropogenic CO2 emissions that go into the Southern Ocean, and about 68% of the entire excess heat. And if you put a number on this, actually, with current trade values of carbon, this is many trillions of dollars that we are talking about here. And through this process, the Southern Ocean slows down global warming substantially. And the other important process here is that it loses heat towards the continent. And we have heard a lot about this yesterday and also today. And that interacts, of course, with the melting ice around Antarctica and contributes to sea level. So this seems to be a pretty clear picture, but actually, if we look at this in detail, we have huge uncertainties in these fluxes. And when we build budgets, we are still sometimes debating the sign of the flux in certain regions. And that's a huge issue, because if we really want to understand the future of climate change globally, we have to understand the Southern Ocean heat and carbon budgets. And most of the uncertainty, I would argue, lies here in this outgassing and heat release fluxes that are in the area south of the ACC, and maybe not so much in the anthropogenic uptake. So when we talk about these budgets, what I was saying, we have made huge advances in the last couple of years and decades, especially with the new capabilities that we have with the SOCOM biogeochemical Argo floats. And in this paper here, you can clearly see where we are or what is the range of fluxes we are talking about in terms of uncertainties. So depending on what product you're using, we are really here having a huge uncertainty, and this will be fundamental to resolve this issue in the coming decades. And for this, Sarah already said that we really have, it's critical that we sustain the biogeochemical Argo array in the first place, but also at the same time sustain shipboard measurements to know what size of flux we are talking about, and to do proper budgets. We can only do by the combination of these data sets. We also have to really sustain the repeat hydrographic sections, and we have to reassess them actually. And for this, I strongly argue for international coordination that needs to be strengthened to get a better circumpolar understanding, especially in winter time. Also, the second point that I want to make is that we have to really close this gap that we have between observations and models. So we can really see here in the global carbon budget that there is a huge mismatch between the models and the data in the Southern Ocean, and we really have to strengthen the effort and prioritize data that helps us to improve models and parameterizations of those. And we also have to strengthen observations in so-called blind spots. And really one of these blind spots is under the sea ice in winter. And this is really where this transformation happens between deep waters that come up to the surface and are transformed to winter waters. And throughout this process, we get a ventilation of CO2 to the atmosphere. And we really have to focus on this processes involved in this ventilation process if we want to further understand this. The second blind spot, so to say, is really the coastal region, and we also have heard about this a lot yesterday, and have to understand how the heat is being transported from the open ocean to the coast, and how the fresh water that's released from the Antarctic continent is leaving the coastal region. And for this, we have to get high quality data of salinity, but also of tracer observations such as isotopes or noble gases, and have to focus on those to better understand how the impact of melting ice in Antarctica affects the ocean circulation, and therefore affects the freshwater budget and the carbon and heat budgets. So with this, I think I'm over my time already, so I'm happy to answer questions later. Thank you.
Thank you, Alex. So our next speaker is Amelia Shevnow. Amelia is an associate professor of geological oceanography at University of South Florida College of Marine Science.
Okay, sorry for the delay. Thank you guys for inviting me. I just really wanted to talk about and emphasize the importance of paleoceanography and paleo records in our sort of understanding of the evolution of Antarctica's system, and being able to put into context the observations that we are making today, and to see if these observations suggest that the system is outside the span of natural variability or within. And so much of what we know about Antarctica's cryosphere evolution through time is really inferred from the deep sea records. And so here is a record of oxygen isotopes in the deep sea from the Cretaceous all the way through to the present. And then these are the RCPs from ICP showing where we might go in the future. And what we can see is that we have a general cooling trend of 12 degrees over the last 65 million years, as well as periods of time where we have rapid ice growth at the Eocene-Oligocene boundary, where we think we have the onset of East Antarctic ice, in the middle Miocene, where we might have the onset of West Antarctic ice, and then this period of time here more towards the present, where we have both Northern Hemisphere ice and Southern Hemisphere ice, and we can't distinguish between these two. And in the isotope record. And what we think drives these long-term climate trends are either and or changes in atmospheric CO2 or tectonic changes. But deep sea sediments really can't tell us where the ice grew and when, how the continental shelf developed around Antarctica that enables the ice sheet to grow towards the ocean. We don't know much about past ice extent. We don't know much about past retreat rates unless we have these Southern Ocean ice proximal sediments that contain records of these past ice-ocean interactions. We are now able to generate ocean temperature records in the past that enable us to understand that temperature at the ice margin. We also are able to get sea ice extent and climate teleconnections. And one of the big things, this is a map of the ice or the sediment cores around Antarctica, as well as drill cores. And what we've really learned in the past couple of years is that East Antarctica is a lot more sensitive than we imagined in the past. And there's about 19.2 meters of sea level equivalent ice in these marine-based basins around East Antarctica. So I want to walk you through some successes that we've had in the long-term record. So this is a piston coring and geophysical survey record from offshore of Totten Glacier. And what we were able to do is really use these high-resolution geophysical records to show us and tell us about ice sheet evolution. And we took piston cores and were able to primarily date those and tell us what we were seeing in the sediment record. What we need to do is we need to drill this area next to see how the ice has evolved through time. We also have been able to do this on the continental shelf. This is IADP Expedition 374, where we were able to generate an ocean temperature record through the Miocene climatic optimum, which is one of the warm periods of time where we expect that we're going in the future. And what we're able to see is that we actually have warming before ice expansion. And this is a record of the sediment showing that ice expansion over a warm period. And so the next steps there that we really need to synthesize records from the terrestrial to the deep sea to understand how ice sheets evolved in the Ross Sea area over the past 14 million years. We also have been able to reconstruct Holocene temperatures through time and really high resolution comparable to the ice core records. And this is a record of sea surface temperature from Palmer Deep. That was one of the first sea surface temperature records around Antarctica. We have many other ongoing records that we're preparing in the Holocene that give different perspectives on how different catchments evolve through time. We can only do this from ships, and we have several science priorities, including really understanding East Antarctica at the catchment scale, understanding past ice retreat rates, as well as being able to really date these records well. What do we need to do this? We actually need a ship to do everything that I've just proposed. To access East Antarctica, we need a longer expedition duration, we need heavy ice breaking, we really need to be able to hold station, and we need to generate high resolution geophysical records, as well as some sort of geotechnical drilling capability. And what I want to emphasize is to do this, we don't need a moon pool. We can do this over the side, or we can do this with the seafloor drilling system. And we need space in the ship that we can use to do shipboard core processing. And so to end, I really wanted to stress that we really need a paleoceanographic and paleoclimate component integrated into all of these large interdisciplinary programs, just like the IPCC did in this rendition, because we need to place the ongoing changes in temporal context. So thank you very much. I'm over my time.
Great, thank you, Amelia. So our last speaker for this session is Sharon Stammerjohn. Sharon's a senior research associate at the Institute of Arctic and Alpine Research at the University of Colorado in Boulder.
Thank you. So we're going to zoom back to the present, more or less, the last 40 years to 100 years. This is fabulous, right? To have this array of talks in one session. So I'm going to talk about Antarctic sea ice variability, the long-term trends, long-term in quotes, and coastal exposure. What is most amazing right now is that we are now going into our 7th year of record low Antarctic sea ice. And there's been a shift, as you can see in this very beautiful figure by Alex Howman, and it's soon to be submitted, so hold on to your hats. But he's showing here that you have the monthly anomalies, and we've had this overall increase in sea ice extent up until about 2015 during the satellite era. And then suddenly we shifted to record low. What else is very remarkable about this transition is that we increased in anomaly persistence and variance. And we then shifted quite dramatically. We don't know why. We can point to atmospheric circulation anomalies for certain, events in the anomalies that appeared in 2016 going forward, but the persistence is what has us flummoxed, and it points to the ocean. We can put this into a longer term perspective. Recently available reconstruction. This is an observational based reconstruction made by Ryan Folk and colleagues, just came out recently. And this is pure gold for us in the sea ice community, because now we can see, beyond this satellite record. And what's remarkable to me is what I see in this record is this underlying trend. It's kind of what the global climate models were suggesting. There's a lot of issues there, so a lot of uncertainty. This is a pretty robust observational based reconstruction. It's showing winter sea ice extent. And this now 6 to 7 year period of record low sea ice is kind of in line with that long-term trend. So it kind of begs the question, what was happening during most of the satellite era that we've been trying to figure out? Well, we have a pretty good idea, and a lot of that's the atmosphere, but I'm going to show you first the spatial map just to contrast, because this actually highlights another really important thing that has changed. And so you're looking at ice season duration anomalies. That's for 2014 on the left. Blue means longer ice seasons. And in 2022, red means shorter ice seasons by up to 3-4 months. I mean, it's kind of remarkable anomalies. But they're also more or less circumpolarly wide distributed, which is very unusual over the satellite record. The satellite record normally shows very high seasonal and regional variability. And so again, this transition from going to record high to record low, and it being persistent, it's also not just persistent in time, but it seems spatially persistent. So again, pointing to the ocean. We also have another new metric that just came out. This is Phil Reed and Rob Massam looking at coastal exposure. And so this is a map showing the trends over the satellite era. Blue means longer exposure. And so here we have all of West Antarctica that's trending towards longer and longer exposures to wind and waves. And I could say that for the last year or two, we've also been at a low for fast ice and at a record high of coastal exposure everywhere, not just West Antarctica. So winds are the conspicuous drivers, right? And we've known this, and it really imprints on the regional and seasonal variability. This is a map just showing correlations between winds and ice motion, also related to sea ice concentration changes. This is very obvious. It's very expected. We have the Southern Ocean that's exposed to the highest wind and waves on the planet. And yeah, we're going to see very strong variability associated with the atmospheric circulation. But what explains this transition that we've just experienced from record high to record low that's in line to the background, decreasing trend? It points to the ocean once more, but we don't know really what those ocean changes are. We can infer them, we can use our models, but we lack the data. And so we really need, especially, and this is just preaching to the choir, but we need the ocean observations within the sea ice zone on the continental shelf at the coast. Because it's the ocean that's driving the changes in sea ice production and thickness changes. And the other thing we don't know very much about are thickness changes. So we're still trying. We have experts in this room who are improving that metric derived from satellite data. It's challenging to measure that in the field. Our ice mass balance buoys don't last very long. So it's definitely a challenge that we need to improve. And of course, the snow on sea ice is a problem. So overarching questions for the sea ice community, for the ice ocean atmosphere community, we're still trying to disentangle thermodynamic from dynamical sea ice processes and the horizontal vertical fluxes of heat, fresh water, gases, nutrients. Alex just gave us a beautiful rundown of all the challenges and gaps that we need to address there. And of course, there's the very strong ice ocean seasonal feedbacks too, that could be playing into what we're seeing currently. So all of these priorities and near-term needs have all been said before, but again, we need those ocean observations in the sea ice zone during winter, especially on the shelves near the coast. We really need sustained observations actually in coastal areas, which are often very difficult to access because they're clogged with icebergs, thick sea ice. And yet that's really a critical boundary and it's changing really fast. So we have a very coupled atmosphere ocean ice system. And in order to really properly study that and improve our models and improve our predictability, we actually really need more multi-platform, multidisciplinary process studies. And so we're combining ships, satellite, autonomous observations together with data model synthesis. We're starting to do that, and it's remarkable. And just this gathering of the community, is also headed in that direction. So the challenge, I'm not going to repeat these because we've all heard them, but if I could just take one more slide, I just want to emphasize that this coastal access is really important. And so this is a map of the MODIS showing the sea ice distributions. We were there, many of us in this room were there last austral summer, and we were trying to get there near the Thwaites, near the Eastern Amundsen, and we couldn't. And this was a record low summer sea ice year. It had all blown into this particular area. It clogged it. We couldn't get to it. The Koreans were there, and they were able to actually access some ice shelf areas and deploy drilling rigs and also deploy XCTDs from helicopter into these critical zones that if we'd had that capability, we would have been tagging seals, would have been a remarkable time series over in the Eastern Amundsen, and we would have been deploying XCTDs. We would have been doing what we really needed to do. We gathered an amazing data set, so no problem with that. But I'm just saying that even in a record low sea ice year, we still need access to the coast. And the only way I know how to do that is with helicopters. Thank you.
All right, thank you. So we now have 10 minutes for questions that we'll read coming in from Slido.
All right, first question, and this is a general. Does the existing ARV as envisioned contain the capabilities for making the shipborne ocean geochemistry measurements as needed? Anyone want to jump in?
Yes, sir.
Or maybe Alex, if he's still on Zoom.
Yeah, I'm still here. There is one thing I want to say to that. So I think we are definitely capable of doing much more analysis from shipboard measurements than we are from autonomous platforms so far. So we still need those for geochemical analysis for sure. But one thing we shouldn't forget, it's important to get the access to the ice and have a strong ship that can break through the ice. It's no doubt. But we also have to consider that we are working in an environment where often the work we do is limited by the weather and the waves. And sometimes we are not able to work while we are at sea because it's just not doable. And so we have to also have a ship that, allows to deploy instruments in very rough conditions and that keeps as stable as possible also for people to do their work. So this is something that we have to consider, especially if we go into the winter season where storms are much more frequent. That's something I wanted to add here as well.
Thank you. Any other comments about that question? All right, next question. This one is for Sharon. It says, you touched on this, but the recent sea ice loss extends about as long as the sea ice growth of the 2000s. Any sense that we're just entering an era of larger magnitude decadal variations, or do you expect sea ice loss trend to continue?
Can you hear me?
Yeah, it's always on.
Oh, it's always on. Would have been good to know, huh? So stay tuned for Alex's paper, soon to be submitted. He's exploring that question. It's the challenge. It's always been the challenge. There's so much variability, and the Antarctic sea ice is so sensitive to that variability. If you want one metric in the Southern Ocean that's going to show you the greatest amount of variability, it's Antarctic sea ice, because it's highly sensitive to the atmospheric forcing and ocean forcing. So, and we know we have very strong teleconnections from the tropics and even the northern hemisphere. So we know naturally we have a lot of decadal variability, and we have a lot of interannual variability with ENSO. We need really the ocean data, and we need time series in order to address that question. But I think Alex is going to be making some progress with the analysis that he's going to present, and it's also going to highlight, where the uncertainties are. So I don't have, Alex, you might want to chime in, but I don't know how we can say we don't know, basically, but it definitely points to a stronger role of ocean forcing.
Yeah, I don't think we can answer this question yet for sure, but of course it's a burning question we all want to know. But yeah, it's just very difficult to answer this, and we have to have a longer time series and better models to be sure what is going on there.
Great, thank you both. For Amelia, can you summarize the capabilities of the JOIDES resolution for working around coastal Antarctica as compared to the new ARV and its future timeline?
Well, that's a question for the ages. So the JOIDES resolution is an older ship, and we are currently in a state where we may not have access to her, but that is up in the air. Ultimately, though, she is not an ice strengthened. Well, she's ice strengthened, sort of, but the captains are quite shy about bringing her into the ice at all. We were able to get into the Ross Sea Pollinia with an escort from the Palmer that we didn't actually need because the ice was so low. On the peninsula, she was able to drill in Palmer Deep with ice support as well. And the sea ice was not very heavy at all when that was drilled. But that's not the case for the Amundsen Sea, and Julia will probably talk about that. And so there's very limited access by the JOIDES resolution to any of the shelf regions. We can access the slope, maybe we can access the larger Pollinias, but she really isn't the vessel to be drilling in the Antarctic. And but we have proven that with simple high RPM and low weight on bit rotary coring that we have been able to recover really incredible sequences that we're able to look back through time and try to understand how the Antarctic ice sheet has evolved. So loaded question. She may not be around for very long, but we really need to get into these heavy ice coastal regions.
Thank you. A question for Ed in particular. Which paleoceanographic records would you and the community like to see tie into ice core records? Are there certain places, certain times?
Well, it's a big loaded question. I think you maybe pick your favorite. The thing that comes to mind when I'm listening to all these discussions here has to do with understanding carbon dioxide variations on sort of century to glacial, interglacial timescales. And there, it strikes me that it's not any one place that matters, but it's actually understanding sort of the four-dimensional carbon cycle of the Southern Ocean. So in the modern, we're still trying to figure out where carbon's coming in and out of the ocean. And the same problem exists on longer timescales. We see individual places where things change and they are compelling with respect to the dozen or so mechanisms that change atmospheric CO2, but we actually don't really know the budget, the balance. So that's one take is we need comprehensive data. And then, you can run down the list. I think the coastal environments and changes in sea ice and understanding whether we really can trace sea ice from ice cores is quite important. And my favorite at the moment is to understand the MPT and the sort of pre-MPT ice sheet, particularly in East Antarctica. I think there's a lot of uncertainty about how sensitive that section is to warming. So, but obviously, if you ask other people, you'll get other answers.
Thank you. Question for Sharon. What kinds of tools would provide the sustained observations in the coastal environments? Is this a ship requirement or an autonomous measurement needed?
It's both. So yeah, we definitely need to improve the autonomous observational platforms for that for actually anywhere in the sea ice covered Antarctic area, because it's such a dynamic region. And I think we're going in that direction, as we've heard from others as well. But I think it really requires that collaboration between engineers and science, so technology. So I'm really happy to know about the new directorate at NSF, the Technology, Innovation, and Partnership. And I think we need to learn how to use that on the science side to improve that ability. But I agree wholeheartedly with my colleagues that you can have and improve autonomous observations, but you still need the ship-based for calibration, for deployment, for retrievals, for the process studies. It's really those process studies. I mean, we need the time series and we need to be able to distribute that spatially, but we need that, what I was describing, the multi-platform, multidisciplinary process study on board that's looking at that strongly coupled system.
Thank you. And kind of a follow-up or a related question. Is there more that we can do to leverage the autonomous platforms to monitor these regions? Are we getting the most out of, for example, under ice Argo or instrumented seals, et cetera?
So again, to tag seals, you need a ship and you need to be able to get into those areas where you can find the seals. And that's a challenge. But I do think, and we have experts here, that the seal data is remarkable, and it's really provided those winter observations under the sea ice cover that we don't have any other platform really. The Argos, those few that have been deployed within the seasonal sea ice zone they didn't stay under the seasonal sea ice zone. So we need to figure that one out too. We can do bottom moorings, but if you really want upper ocean observations, you're now at risk of icebergs and thick ice dragging these along.
Thank you. Question for Alex. One of the needs you pointed to was better ocean salinity measurements. How do these requirements relate to the currently available salinity retrievals from satellites? How much better accuracy and or spatial resolution is needed?
Yeah, thanks for asking this. I think it's really important that we have very high quality salinity measurements in the Southern Ocean, because it is what determines the stratification of the upper ocean. And the gradients sometimes are small that we are looking at. And so we really need high accuracy salinity, and also from the autonomous platforms that needs to be improved, certainly, I think. And you are also pointing towards the satellite, and I think that there is also some potential there that we can learn on the larger scale variability also around the ice edge, or maybe in Polynius from satellite data. And I think that's a very emerging topic that is still, I think, progressing, but I think also satellite data in the marginal ice zone is becoming better and better. And I think that will be also in future a great tool to have.
Thank you. We'll stop there with questions.
Yeah, I think our time is up, but if we didn't get to your question, those will be useful for the committee. So please do submit questions. So that finishes this session. Thank you to all the speakers. We're going to move directly into session 5, and that one is going to be moderated by Dan Costa. So the speakers for that session, please come to the stage. Thank you, everyone.
Yeah, this is going to be a great session. We've had a series of talks providing the context for the biota. And so now we're going to look at how Southern Ocean high latitude biota and ecosystems have evolved and how they respond to and contribute to systematic change. Our first speaker is Eileen Hoffman. Eileen is a professor and eminent scholar in the Department of Ocean and Earth Sciences and a member of the Center for Coastal Physical Oceanography, both at Old Dominion University. Eileen?
Okay, thank you. Do I need to do something here to? Okay, wait. Okay, thank you. First off, I'd like to start by thanking the committee for the opportunity to be involved in this workshop, and it's been interesting discussions for the last day or so. All right, so what I was asked to talk about was Antarctic biota and ecosystems and where we might be in the future in terms of observing these systems and what the systems might actually look like. So I'll start with a reminder here about observations. And we've heard from many of the speakers and in various discussions that there are multiple observational platforms available to us now, and ships are only one of many of these platforms. So we heard from Oscar yesterday that the ship capabilities should allow interfacing with other platforms and advancing science. And here I'm talking about in terms of ecosystems and other things as well, requires integration of all of these available observing technologies. All right, so we talk about food webs or ecosystems in the Antarctic. The figure shown to the left here is the iconic Antarctic food web, where everything flows to Antarctic krill and everything flows outwards from Antarctic krill. So this is the food web most people have in mind when they think about Antarctic ecosystems and biota. The center panel here is an example of a food web from South Georgia, a subantarctic area of the Scotia Sea. And the food web to the left here is the krill-dominated food web. But the one to the right is a non-krill dominated food web, because at times South Georgia runs out of krill, in effect, because it's dependent upon inputs of krill from upstream sources like the West Antarctic Peninsula. The point here is that you can shift to a new food web. And in the case with South Georgia, with the non-krill food web, that can sustain the system for a little while, but in the long term, it does not support all the top predator trophic levels that like the seals, the penguins, and the whales. And I bring this up because what we're seeing now in some areas outside of the subantarctic or the area and the Scotia Sea is a transition to this non-krill dominated food web. The panel on the right here is from the Ross Sea, and that's another type of food web where krill is not the dominant mid-trophic consumer there, or mid-trophic level organism. There are various other organisms that come in there, and how we shift between those has lots of implications for the food web. So we have a lot of heterogeneity in the forcing and habitat structure. We have a lot of regional differences, and that's another thing to think here about. Is it's a different food web depending on where you are and the type of and the season. All right. The other thing is Southern Ocean or Antarctic food webs are not isolated. They're globally connected, and they're connected at different kinds of trophic levels. The seabird and cetacean migrations in and out of the Antarctic link the Antarctic food webs to those at much lower latitudes. So that we have so in the Antarctic, there are a lot of seasonal residents that are of the high latitudes, but also of the low latitudes. And Dan Costa and his colleagues recently extended this idea by looking at the carbon and nitrogen transport that occurs through these seasonal migrations in and out of the Southern Ocean. There are also human interactions there that also give global connectivity, mainly through fisheries and tourism, that both of which have impacts on the food webs. And so the changes that go on in the Southern Ocean food webs have consequences outside of the Southern Ocean. And so what we want to do is to look at what these might actually be in the future because of looking at conservation and management of these systems. All right, so I was asked to look into the future and see what that might hold for Antarctic food webs. And one way to look into the future is to use projections. And we're very fortunate in the Southern Ocean to have a number of high resolution regional and circumpolar coupled circulation sea ice ice shelf atmospheric models that can be used as input to food web models, biogeochemical models, and habitat models. And I've just shown you two examples here. The one on the right side is a circumpolar, high-resolution circumpolar projection for temperature, and the one on the left is a regional one from the Amundsen Sea. It's a circulation, but you see it resolves a lot of the mesoscale variability. So we have these models, we have these tools. All right, so if we implement this is from a recent paper by Mike Denneman, looking at projections of sea ice concentration. And in the left panel here, the uppermost thing is the current condition of sea ice. The one to look at is for 2100. And you can look at that and see we have a huge reduction, projected reduction in sea ice. The center panel here is a projection of ice shelf basal melt. And this is done as a ratio of the future 2100 to current. And this suggests that there is an increase in the basal melt rate of many of the ice shelves. And that's related to things we were talking about yesterday with warm deep water coming in onto the shelf. So in terms of the food web, that's what the right panel here shows. There's going to be a large increase in dissolved iron. And Southern Ocean ecosystems are limited. The primary production is limited by the availability of dissolved iron. And so the projections suggest that there's going to be a lot of dissolved iron available to the surface waters in the future. All right, so that would suggest that there's going to be an increase in production. All right, so if we look at an example from the Ross Sea, looking again at projections, and here you're looking from the Ross Sea out, ice shelf out into the Ross Sea. And the panel on the left is a projection for 2050. And the thing to look at here is the orange and red colors. All right. And this is a projection of mixed layer depth. All right. And so what this suggests is that mixed layer depths are going to get deeper. So there's more mixing, which allows more of the dissolved iron to come up into the surface waters. And by 2100, there's a lot more mixing with much deeper mixed layers. And these are for the summer period. So there'd be reduced sea ice is what's allowing this to happen. There's more open water for longer time, which means a longer growing season and increased inputs of dissolved iron. So in this particular paper, they went ahead and looked at the primary production, and there is an increase in primary production, but what changes is that there is a shift in the phytoplankton community composition to diatoms, and that has implications for the inputs to the food web. All right, so this would suggest that maybe, it's going to be great. Lots of primary production, lots of iron stimulating the production. But what we really want to do is say, okay, what happens next? So the projections for the rest of for other components of the food web, and here I've only picked two, for Antarctic krill as an example, if we look at projections, the one on the left side here is a projection of krill growth potential. And this was done using the some of the RCP scenarios. And the thing to look at is the red line. And in the summer, that line is collapsed in up against the coast. All right, so these are areas that are favorable for krill growth during the summer. The green areas are ones where krill do not do well growing during the summer. All right, the center panel here looks at projections of krill habitat based on the ability of the krill to complete its reproductive cycle. All right, and the important part here is to look at the orange areas relative to the green areas. So the habitat becomes much smaller to where krill can actually complete its reproductive cycle. And one of the strongest constraints you can put on an organism is the ability to either complete or not complete its reproductive cycle. All right, so if we look at a crab eater seal here from a recent paper by Louis Huckstadt, this is projections of seal habitat along the West Antarctic Peninsula in terms of where the seal has the ability to forage, particularly during the time period when they're getting, when they're pupping and that type of thing. But this is looking at the austral summer. And what this suggests is that there is a big habitat change and that the habitat that can support the crab eater seals is going to shift to higher latitudes. All right, so these would suggest that the other parts of the food web are going to have to move, and they may not be moving into areas with increased primary production. All right, the other thing I want to mention here is marine protected areas. The center panel shows the existing and proposed marine protected areas for the Southern Ocean. The one on the right here is the marine protected area that is now in existence for the Ross Sea. All right, these areas are becoming set aside, and the Ross Sea one, which I think David Ainley will talk more about in his flash talk, are areas where we need to have monitoring and research. All right, the Ross Sea MPA is in existence for 35 years. At that point, it's going to be evaluated to see if it's effective or not. The only way we're going to know that is whether or not we do, whether it is by monitoring and looking at that system. The figure on the left here is from a workshop that Sharon Stammerjohn and others ran recently, looking at what is needed to monitor and evaluate the Ross Sea MPA. And the bottom pillar of this is observations, but also observations connected with process studies. So that's fundamental to understanding these areas and having access to these areas at all year round, or certainly at more than just the austral summer is important for that. All right, I would be remiss here if I don't briefly mention here the UN Decade, the Southern Ocean Task Force. There is a Southern Ocean Action Plan that was recently released about what the research needs are in the Southern Ocean. This is an international program. The action plan goes through many different things, but the one thing I want to talk about here is what's highlighted in bold here is one of the recommendations from this is to have a coordinated international circumpolar sea ice study with a focus on seasonal and regional variability. The rationale behind this is that many nations are now having platforms, ships and autonomous vehicles that can measure sea ice environments. But also, as Sharon just pointed out in her talk, sea ice is changing. And what we know is that sea ice is going to change a lot of things, and marine ecosystems are one of the things that will change. All right, so to sort of end here, we have a complexity of responses here. They're all shown here. There are a lot of interactions, and these stressors are going to interact in like warming and acidification are going to interact in various ways to change our marine ecosystems. And we want to be able to monitor that so that there can be some type of adaptation or mitigation. All right, so challenges. Observational capabilities. We know there's going to be reduced sea ice, or we think there will be reduced sea ice and increased open water. That puts more emphasis on coastal environments. And it also puts emphasis on higher latitudes as food webs shift. We need to have inclusion of new data and technologies, the omics work, which I think Allison will talk about, as well as integration with remote sensing and autonomous measurements. But importantly for the science we're going to need to think about neglected trophic links, because what's neglected now we don't study may in fact become the major trophic pathway later. Also adaptation pathways. And I'll come back to the fact we're using projections to look at this. We need the observations to improve the projections. And this came up yesterday, is that you couple the observations and models while at sea, run the model to help you guide your observations. So I'll stop at that point and say thank you and look forward to questions. So thank you very much.
All right, thank you, Eileen. We'll now have 3 minutes of questions from Slido. Do we have some?
We don't have any in Slido yet. So if you have a question, please add it to Slido.
They're too intent listening to the talk.
All right.
Oh, there's an in-person question. Can we get a mic over to Mo?
You mentioned in your talk that there's a shift in the primary producers to diatoms. If it's not diatoms, what is it? Like, what's the other option?
Right now in the Ross Sea, a lot of it is in Phaeocystus, which is a type of phytoplankton that doesn't really, it's not easily grazed by a lot of the zooplankton. And so potentially by shifting everything to diatoms, it would encourage something like an Antarctic krill to come in there and eat, because Antarctic krill don't really eat Phaeocystus.
So they're just like some kind of teeny tiny microplankton?
I'm sorry, what?
They're just like a microplankton, like what kind of organism is a Phaeocystus? Is it bacteria? What is it?
That eats Phaeocystus?
No, what is it? What is Phaeocystus? What kind of organism is it?
I'm sorry, I'm having.
It's just.
That eats Phaeocystus?
No, it's fancy.
Oh, what type is, it's
Mesiophyte.
I'll let Tish answer. She's the expert. Yeah.
I believe it's a promesiophyte, which is a different kind of protist.
Thank you.
All right, and a question from Slido? Okay. Go ahead. Could you elaborate on what key observations are needed to evaluate the effects of the Ross Sea Marine Protected Area program?
Whoa, we just had a whole workshop on that. There's a workshop report that elaborates on some of that, but I mean, the physical environment for sure. And then just documenting or measuring food web components. Yeah, that it's basically looking at the food web and then how that food web is responding to things like not allowing fishing vessels to come in. Does that, what's the impact of that on higher trophic levels? And I think David Ainley might mention some of that in his presentation. But, yeah.
Thank you. Ted?
You mentioned that the iron content in the coast will be rising in the future. I assume from basal melting. In that model, do you know whether or not they accounted for varying iron content in the ice that's being melted around the top?
No, that is not in the model. What has been used is an average in member concentration for the ice, for the dissolved iron that's in the melted ice. But that is a very good point, and that's something that could be incorporated at some future time if the information is available to do it. Mhm. Yeah, and I should say we could change those projections by changing those kinds of numbers. Yeah. Yeah, thank you.
And one kind of also a question related to iron. How good are the predictions of future iron flux to the surface ocean, and what might be needed to improve those?
Yeah, okay, so the predictions of the flux to the surface ocean are based upon the circulation models and also the circulation underneath the ice cavity. So if there are observations that improve how we can parameterize and simulate those processes, that would improve the projections for the amount of dissolved iron that will be delivered to the surface waters in the coastal environment.
Okay, we're going to move on now. We're going to start our flash talks. We'll hold the questions until the end of all the flash talks. Our first flash talk will be given by Allison Murray. Allison is a molecular microbial ecologist and biological oceanographer at the Desert Research Institute in Nevada. Allison.
Hi, thank you. I wanted to thank the National Academy and the committee for inviting me to share a few thoughts on future research directions in biological adaptation and evolution of life in Antarctica and the Southern Ocean. And I need to start this off with an acknowledgement that these ideas come from a workshop that we had in October that NSF sponsored. And so I really want to thank the participants to that workshop. There were about 60 that were there. It was all virtual, and the organizing committee who's been working with me to sort of synthesize the data since then. If I think that there's consensus that if we have to distill things down to one driving question regarding life in Antarctica, I think it is, what is the resilience of Antarctic life, scaling from viruses to whales to changes brought on by climate change? There are some example types of questions in this area of research are, how are Antarctic population genomes structured over space and time? This tells you about how diverse the populations are, and how diverse they are can tell you how resilient they are. The more diverse ones tend to be more resilient. How fast can Antarctic genomes change? Something that we really don't know. How competitive are Antarctic organisms to invasions in terms of predation, competition for resources, space, and disease resistance? And how sensitive are Antarctic organisms and ecosystems to human-driven pressures, such as fishing, tourism, our human presence in Antarctica? This requires collections of diverse species, many members of each, experimental research, ecosystem studies across the Antarctic and Southern Ocean environments by a diverse population of polar researchers. Each species may respond differently to environmental pressures, and each may adapt, evolve, and respond differently to changes in climate. As you may or may not know, DNA encodes genes. These are the words that encode functions of the proteins. These are like molecular machines, and selection happens at the level of these molecular machines. And those changes, though, are recorded in the genomes. Antarctica, I have not a lot of time to talk about diversity, but the diversity of life in Antarctica is immense. It is, especially in the marine ecosystems, it approaches that of what we find in lower latitude ecosystems, but we know a lot less about the life histories of these animals and their evolution, how they've adapted to the Antarctic. Genome sciences, comparative genomics are really starting to shed light on the molecular basis of biological adaptation and response. And although there are maybe 17,000 invertebrate organisms that live in the benthos of Antarctica, we, in a sort of an unaccounted for number of microbes and single-celled eukaryotes, we're beginning to know something about certain areas of based on genomics in this area. Antarctic, the fish community has sequenced now 44 fish genomes of the notothenoids, which are a very interesting population of fish that really expanded and radiated, are very successful in Antarctica. And through their genome sequencing, we've learned about genome expansions that have then, where antifreeze proteins are present in multiple copies. Proteins, membranes, and metabolic adaptations are all found and identified through these comparative genomic studies. A lot of the enzymes can have very small numbers of changes in them to make them cold adapted. So in the figure in the lower panel, structural adaptations for just 3 amino acids have enabled this protein, adenylate kinase, to be really flexible and still perform at low temperature. There are about 8 Antarctic algae genomes that have been sequenced, and this sort of early stages of research has shown that there's hundreds of duplicated genes. They have ice-binding proteins, and they have restructured photosynthetic apparatus. In some cases, a number of genes have been duplicated for light harvesting pigments. There are numerous cold adaptive features in bacteria. This diagram shows some of them. There are many more bacterial genomes that have been sequenced. They're sort of small, on the order of sort of 3 to 5 million bases. And they're pretty easily accessible through either sequencing of isolates or sequencing of metagenomes. But they have cold shock proteins. They also have ice binding proteins and many adaptations to their membranes to allow them to function in the cold. The vision for Antarctic omics science in the 2030s, and omics is sort of the combination of genome sciences, transcriptome sequencing, proteome sequencing, metabolite sequencing, or metabolite chemistry. In order for where our vision is that we think that there's going to be hundreds of genomes for eukaryotes, thousands of genomes for fungi and algae, and other protists, tens of thousands of genomes for bacteria, archaea, viruses. This needs to be linked together with an interoperable cyber infrastructure system that does not exist currently. And to study the behavior and adaptation of these organisms, we can use transcriptomes and other types of omics to really look at the functions of their adaptive responses. An important point here is the integrated understanding of ecological and evolutionary interactions between trophic levels, functional networks, and ecosystem function are needed to develop this comprehensive vision of what is happening in Antarctic organisms and ecosystems. With this information, in order to access it, ARV-enabled access is critical, and so many of the points that have already been brought up and getting to different ecosystems also include the hydrothermal vents and cold seeps, and really understanding the gradient of coastal to polar frontal zone oceanography are important. Climate, a lot of people in the community are really interested in doing, in order to study adaptation, doing onboard experiments is critical. So having the facilities on the ship to facilitate experiments is important. Having an enhanced presence to seasonal access, year-round access, key. Incorporating omics into informing Antarctic MPA research, like what Eileen introduced, is going to be important. And really integrating ecosystems research, tying together trophic levels, physiology, omics-informed science. And I think that in a lot of the platforms that were described yesterday, for solid earth and for sea level rise studies, you can also incorporate life scientists on your cruises to help and take advantage of the types of ecosystems that you're working in and access, especially to the benthos. Thank you.
All right. Thank you, Allison. Again, we're just going to move right on and hold questions for the end. Our next speaker is David Ainley. David's a senior avian ecologist at H.G. Harvey and Associates in Los Gatos, California. David? Is he muted?
Hello?
Oh, there he is.
We can hear you now, David.
Okay. Well, I'm really honored that I was invited to talk about this sort of thing. The question I was assigned is interesting. Most of the talks we've heard so far have been confined to climate change. However, recent work in the Southern Ross Sea has shown that, yes, indeed, climate change is important, especially wind-driven factors, but also the food web is changing, and it likely has to do with fishing. And it's showing that so-called indicator species, such as penguins and seals, their populations have been growing in the last couple of decades. Okay, next slide. So these trends, along with studies of the benthic biota in the Southern Ross Sea, represent the longest biological time series in the Southern Ocean, beginning in the 1960s. This is an incredible archive of data from which the present and the future can be based. The trends in the Southern Ross Sea should not be dismissed as anomalous. The Southern Ross Sea represents the high latitude Antarctic. So these penguins and seals have been designated by CAMLR as so-called indicator species for the purpose of managing the recently designated Ross Sea region marine protected area that Eileen mentioned. Ross Sea, and particularly McMurdo Sound, is the most intensively researched stretch of the Southern Ocean. There are many hundreds of published studies have been produced, and books such as Biogeochemistry of Ross Sea by Dunbar and DiTullio, and Linia's Windows to the World by Smith and Barber. This is an incredible archive of information. The Ross Sea region MPA was initiated by US scientists. And it never would have happened if it hadn't gone all the way to the US State Department. This designation of this area is a huge deal. And the US has an obligation to be leading the research and monitoring that is required by designating documents. As Eileen mentioned, the MPA is up for renewal and not that far in the future. Okay, next. Please. Slide. Oh, so here is the Ross Sea region MPA. The really nitty gritty is confined to the waters overlying the shelf and slope. All that stuff to the north was added for biopolitical reasons. It is the shelf and the slope in which this incredible archive of information is available. And as I said, Ross Sea is not wanting for so-called indicator species. Okay, next slide. So in my humble opinion, and I do think I'm speaking, and I know I'm speaking for dozens of scientists, the US marine research over the next few decades needs to include a respectable leading effort in the Ross Sea region, and especially in McMurdo Sound. Next, please. Not only that, well, you know, the US will be contributing all kinds of satellite imagery and automatic weather station data to monitor the biophysical factors. You know, the US has been doing this and will continue to do this. However, we have this problem of the indicator species, and they are showing that the ecosystem is changing. But the question is, you know, what is going on? Okay, next, I think. So in McMurdo Sound, the annual cover of Fast Ice provides an incredible research platform to which human divers, ROVs, ice fishing, moorings, tagging of animals, time depth, you know, logging of animals, has been deployed since the 1960s, along with the aerial surveys and that sort of thing. As I said, resulting knowledge is amazing. And so, you know, in a way, there's been a non-official LTR, but now there's a need to be, you know, integrating the various components of what has been monitored for these decades. Okay, next. Okay, here we go. McMurdo Sound, covered with fast ice, but also there's the McMurdo Sound polynya. Thus, the southwestern Ross Sea and McMurdo Sound represents a microcosm of the high latitude coastal Antarctic Ocean. And I've tried to say it's full of indicator species that have been intensively studied, but now their interrelations need to be linked. Okay, next. Okay, so you saw those food web models that Eileen Hoffman revealed. Well, in the southern Ross Sea, the predators and the fish haven't read these papers. It's a very tight food web. I should say that a lot of the phytoplankton goes ungrazed because of the foraging by all these predators. So whether or not future increase in productivity is going to have any effect, it really remains a huge question. Okay, within the food web, we have, which is where silverfish are an important component. We have these species competing with one another for silverfish, but they're also eating one another. So it's an incredible food web for sure, with the arrows going up and back. Okay, next. Okay.
David, we're going to need you to wrap up, please.
Okay, so everyone talking about international collaboration, but we do need an intra-national research effort to be integrated, not just NSF, but also the U.S. Coast Guard, National Marine Fisheries Service, and other agencies. And so, you know, anyway, that's what I have to say. Thanks.
Thank you, David. Okay, again, we'll move right on and save the questions for the end. Our final speaker is Patricia Yeager. Patricia is a professor at the University of Georgia, Department of Marine Science.
Okay, great. Thank you. It's a pleasure to be here. I'm really honored to be invited, and thank you to the organizers. I am supposed to speak on the ecosystems, but focusing primarily on the biogeochemistry. So I'm going to focus on some key questions that have been around for a while. Is what is the role of Antarctic coastal and nearshore regions? We heard a little bit about the open ocean earlier today. What is the role of these regions on the total carbon uptake by the Southern Ocean now and in the future? And we've known for a while that coastal polynyas are carbon sinks because of their very high productivity associated with the marginal ice zone. The Amundsen is the place I've been, and we've shown that its rate of uptake is about 10 times per meter squared on average than the greater Southern Ocean. So these are hotspots. I like to say they're small but mighty. We've also seen from other investigators that the Ross Sea polynya and the Mertz polynya and the Gerlach Strait are similarly potent, if not even more so in certain areas. So this is a really, really important system. And the key is that they're climate sensitive because they're very tightly coupled to the sea ice issues that Sharon Stammerjohn spoke about earlier today. And again, it's because of they're really driven. This is a glider data from Oscar, sort of showing where the high chlorophyll is in that warm, fresher layer that forms when the sea ice melts. So there's this sweet spot where the nutrients and the iron are coming from below, but the water column is stable because there is sea ice melt. And so that's a really important piece of this puzzle. And part of the story about whether more iron is going to make this system more productive is very much related to whether or not there's still going to be some stability left provided by the sea ice. We do know that when the sea ice starts to go away, we can see the flux, the carbon flux of these regions is responsive to the loss of sea ice. Thankfully, the LTR time series data have proven that these fluxes are sensitive to ecosystem change. In this case, you see an increase in the CO2 uptake by this region as the sea ice is still present, but has increased in area, and the blooms are responding. So what else might it be sensitive to? You've probably seen this figure. Maybe you, though, haven't noticed that there's a plankton bloom offshore. And so we've been studying how in the Amundsen Sea, this very productive algal bloom is linked to the offshore, not the offshore, the buoyant melt plume from the melting ice shelf, the basal melt that was just described. And you can see here sort of a plume of iron-rich water coming out from the Dodson ice shelf from measurements made in 2010-11. You've also seen Kevin Arrigo showing that these chlorophyll concentrations across all 45 polynyas in the Antarctic are related, sort of, to the basal melt rate. There's a correlation of about 0.6, which is pretty good. However, if you actually look from year to year, these regions are very highly variable, as are the polynyas. So if you look at the Dodson meltwater flux against the Amundsen Sea primary productivity, they don't match. So it's not a one-to-one. It's not going to be easy to say more basal melt, more productivity. The variable meltwater does not explain these variations. So we've been exploring quite a bit how this actually works, and looking at how combination of sea ice, glacial melt, coastal ice scape changes will be influencing both iron and carbon supply to the coastal Antarctic ecosystem. And just to give you a little bit of a preview, there's iron-rich circumpolar deep water. So in addition to our intuition about, oh, there's iron in the glacier, actually, if you looking at the model, most of the iron that's being brought into these ecosystems is coming from the deep water, the circumpolar deep water that is being meltwater modified and made more buoyant and coming up to the surface. That's a really key piece of the puzzle. It's not just the melting glacier, but in fact, it's the ocean circulation, which is delivering the iron to the surface. It's also picking up a lot of iron as it moves onto the shelf, we think. And then it comes slamming out of the ice shelf in places like the Dodson outflow and entering the polynya through various mechanisms. And then we also realized that there's a really strong coastal current, of course, as you saw in Mike Dinneman's model, that carries stuff from upstream, from glaciers melting upstream, and then carries some of that iron downstream. So it's a pretty complicated system and very tightly coupled to the physics. And you can't just measure the dissolved iron, you have to also measure the organic compounds that might hold the iron and make them bioavailable. You have to look at particulate iron, in addition to the CO2 and microbial communities that are really key to the cycling of this iron and how bioavailable it is. It's not just total iron, but what is the form of that iron, making it available to the phytoplankton. So we need to look at how the iron is coming up off the sediments, and how it's being modified in the cavity. And so tracing what's happening inside the cavity turns out is probably really important, including potential subglacial meltwater contributions coming up from underneath the glacier. So, and then finally, how do you get that iron from that outflow out into the euphotic zone? So there's all the mesoscale processes that you need to understand, and the speciation question that I mentioned. And I am running out of time, so I'll just show you this. We're interested in the coastal ice cape because it's changing dramatically. This is a shot we took this past year of the Western Dotson ice shelf, where the outflow is coming out, and comparing that to the inflow, the eastern side where the inflow is. And I guess you can probably see the caves and the erosion and the slumping of this area where that warm water is coming out. And that's affecting not just the ice shelf itself, of course, but also the ice cape around that area. So what does the future hold? In order to make any predictions about this, we must work with models, as has been mentioned many times. But we really want to know how this productivity and carbon uptake will change with increasing sea ice and sea ice melt, because we may be adding iron, as I said, but if we're also losing sea ice, we're going to lose that mixed layer depth effect. And then I mentioned the subglacial meltwater. So again, working with models, very tightly relationships between the ship and the modelers. This model was built, Pierre Saint Laurent, with really well-validated model data from 2010-11. And it's in the process of being improved with ship data from 2022. But the main thing, I guess I really want to say is, well, I'll show you that model. I'm not going to show you that model right now. The issue I think I really want to point out is that the work we did at sea was very tightly coupled to model, and the model guided what we did. And then we did a lot. And I think we were the example that you saw earlier from Tim yesterday, but we had 2 sets of CTDs, we had underway towfish, we had continuous underway sensors on the ship, we had gliders of various sorts. We had 6 gliders and 2 AUVs. The AUVs went under the ice to get samples for us, which was extraordinary. And then we also, strikingly for the first time, had a trace metal team working next door to a sediment coring team. And we figured out how to do that in a way that really worked. And so what we're talking about is a huge amount of work, a lot of talented people, a lot of really good gear. Many of these things, someone asked about the trace metal system on the ARV. It looks like it's about the same from what I can tell, and I was going to check with Amy, but it looks like it's a similar design to what we do on the Palmer, which is to have the starboard A-frame put the second CTD over the side. So it looks very similar. I also want to emphasize how important it is for the whole group to have support from satellites. Both ocean color and sea ice are critical to our understanding when we're in the ship offshore. And so bandwidth, of course, and getting that information to the ship is key. And then in my remaining minute, I guess I've lost my remaining minute, but let me just say one other thing that's I think is really important and nobody has mentioned. When you put this many people on a ship, and there were 63 people on the boat for more than 60 days, there's a lot of stress and a lot of challenges. I'm not sure we need longer ship time. I could say we could use probably a few more scientists. I do appreciate the increased number of science berths, but I don't think we need more than 60 ship days. We do need 24/7 operations. So we need a team of logistics on the ship that can handle a really, really busy day-to-day process. But we also need, because these teams are interdisciplinary, they're usually international, we come from different science approaches, we need a lot more emphasis on what I think Google has figured out with Aristotle, is that a good team needs help. We need to learn how to function as a team. And so we need more pre-cruise team building. We need more interaction ahead of time between the ships and the logistics people on board and the science. And we need a safe space. The number one predictor of success for Google's Aristotle team study was psychological safety. And so we have to make these ship spaces that are going out for so long safe for the people on board. And that's going to take some work before you put them on the boat. And I will end with that. Thank you very much.
All right, thank you. That finishes our presentations. We're now going to go into the question period. And
We'll do a few questions.
yeah, we'll do a few questions.
All right, we'll just make lunch a little bit shorter. Just a couple questions. The first, relating to the marine protected area in the Ross Sea, what metrics will be used to determine success? And anyone can feel free to jump in.
Can you say that again? I'm sorry.
About the marine protected area in the Ross Sea, what metrics will be used to determine success?
Leave it here.
Is this on here? Yeah, okay. I think the metrics that determine success are still being, still being discussed.
Yeah.
And that's, I think one of the things that came out of the workshop that was held, that Sharon and other people convened, was we're not sure yet what the metrics will be. And Sharon might want to add something to that, but and to me, that's somewhat distressing that the MPA is established and it's there, and we still don't have a plan for how we're going to monitor it and assess its effectiveness. And anyway, other people might want to say something.
I could say something. I tried to make the case for McMurdo Sound. It's a microcosm of a coastal high latitude Antarctic. The logistical capabilities there are incredible. Helicopters, tracked vehicles, snowmobile machines, and that sort of thing, as well as remote sensing from satellites. And so we have this incredible backlog of information of these time series of both the benthos and the water column processes. So really, the MPA was established to quote unquote protect the structure and function of the Ross Sea ecosystem. Well, I don't know that the Ross Sea ecosystem structure and function has actually been described. But I think by integrating these long time series with interdisciplinary work, or at least to continue that sort of thing, I think will go a long way towards seeing, how the so-called structure and function of the Ross Sea ecosystem has changed. If we disperse all our effort way out, far afield, really and with snapshot sorts of studies, it really won't work. But we do have we do have the capability of integrating some incredible efforts. And I would hope that should be encouraged.
Great, thanks. Sharon, you want to make a quick comment?
Okay, one other question. Allison, what is holding OMIX back? Is it just access to the coast? Or sorry, is it just access, or is it the cost of sequencing so many samples? This question's for Allison. What is holding OMIX back? Is it just access, or is it the cost of the sequencing the samples?
It's probably a little bit of both. I think if you ask the community, that access is the biggest problem. The cost of sequencing has dramatically changed in the last 7 years. So that sequencing genomes and doing high quality, the challenging, microbial genomes are pretty accessible to sequence, but now sequencing genomes of eukaryotes with all of these chromosomes and rich character, and really a lot larger scale, the order of magnitude of sequencing, eukaryotic genomes scales from somewhere between 10 to 100 to 1,000 times as big as a microbial genome. So the technology for doing this and assembling high quality reference genomes exists now, and they're doing it. And you may have heard of the Earth Biogenome Project, but this is a very ambitious effort to sequence representative species of all life on Earth. And so through this group and workshop, one of the things that we're interested in doing is being an Antarctic node for that project. And they're pretty eager to have us participate. So I hope that answers the question.
Thank you. And this question is for all. And this will be our last question. Other questions that were entered on Slido, we will ask the speakers to address separately, or our committee will get back to the askers. So the question: the southern Ross Sea McMurdo Sound seafloor is likely to have hydrothermal vents and methane seeps. From the biological perspective, what is the level of importance for exploration of these areas?
They might provide a lot of iron to the bottom water, for sure. So I'd be really interested to know how extensive they are and what their fluxes are, for sure. Not to mention the ecosystem aspects, of course.
And understanding how these systems function in high latitude and in the cold waters and the types of life that live there, and exploring them, I think is super important.
All right. Well, thank you very much. That concludes our session. We have a short break for lunch. It's in the great room. And please return here at 12:15 for our afternoon session. Thank you.
Thank you. Jill.
Yeah, we were on Zoom together a couple of.
Oh, right. Love it.
For the Dale of Hiawatha.
Oh, yeah, that's right. Oh, that's right. Why do you think that kept on? I mean, I think these are on, but can we chat a little bit? Sure. Yes. I mean, I don't understand.
The fact that when it became clear that the age was really much older, I think
That's what's
Blanc just got, basically. Right. So maybe there's a self-population that's continuing.
I think, yeah.
Yes.
Hey, John. You guys can sit wherever you like. All right, who are we missing? We need Sean. Oh, Sean's online.
So
Julia.
Big green arrow forward.
Yeah.
Red bombs upwards.
Sometimes it's a little bit of that way.
Okay, so patience.
Yeah.
Okay. I'm regretting having so many bills now. Thank you.
She just got started. She's here. Sorry. Okay, so. All right, welcome back, everyone. My name is Jill McCookie, and I will be moderating this next session. Our last session today is focused on what changes in erosion and hydrology are expected with shifting ice sheets and how this will affect biogeochemical cycles, biota, and potential hazards. Our first speaker is Sydney Hemming. Sydney is an associate professor in the Department of Earth and Environmental Sciences at Columbia University. Thank you, Sydney.
I'm actually a professor, and that's a good indication of my not having weighed in quickly enough with my bio. Anyway, I really appreciate being here. It's been really exciting to see all the other talks, and I have to say that what my group and I will be doing is piling on with some of the very similar stuff that's been already said. I'd like to start with an overview of sort of what's known about the Antarctic continent, even though it's been said a number of times already, because our task is an overview on changes due to altered erosion and sedimentation. So this is a set of figures from a Pollard et al. Paper, and the top map is it shows the extent of floating ice shelves in blue, and the range of places where the grounding line retreated to that spot within 5,000 years in the modeling simulations. The bottom left figure is the modern bedrock elevations below sea level around Antarctica, and the right-hand bottom is the modern ice thicknesses above flotation. And it's been said a number of times, but the East Antarctic ice sheet holds approximately 52 meters of sea level, something on the order of 18 meters of those that are in this vulnerable place with ice floating, ice margins below sea level. The ice thickness is approximately 3 or 4 kilometers, and it's mostly grounded above sea level, but with these vulnerable spots and wilts in Adelie Land. And in contrast, the West Antarctic ice sheet holds about 5 meters of sea level. The ice is about 1 or 2 kilometers thick on average, and it's mostly grounded below sea level. So in addition to this sort of look at Antarctica and the situation of the ice on the continents, we also have already been shown this famous figure from Zakos et al. Of the Cenozoic climate history based on, this is a shout out to scientific ocean drilling. This type of graph would not be possible without scientific ocean drilling. And in this figure, Zakos et al. Compiled the benthic delta 018 values to look at the sort of global integrated climate history. And notably, at about the Eocene Oligocene boundary, there's a sharp increase in the delta 018, decrease in temperature, but sufficient that it couldn't have been just explained by changes in temperature, and there must be ice volume changes. And this information is largely consistent with the much more sparse data close to Antarctica on the changes in clay mineralogy and ice-rafted detritus, and also sparse studies on the continent indicating about that time for the initiation of Antarctic glaciation. So one of the big questions we have to ask ourselves is how to assess the vulnerability of Antarctica's ice. And this map is a compilation from Brendan Riley of the cores that are available at the Oregon State Antarctic Core Collection. The bigger of the beige spots are cores that are greater than 3 meters, and the bright red spots are cores that are taken that are greater than 3 meters from the Palmer and Gould vessels. And then the drill cores from Andrill and Shaldrill are shown, that don't show up so well because they're in a mass. They're shown in the orange squares. And then importantly, DSDP, IODP, ODP, IODP cores are shown as the yellow squares with red spots around them. I'm going to be showing a couple of examples. Oops, sorry. I'm going to be showing a couple of examples from some of the IODP sites around Fritz Bay and Wilkes Land. Okay, so the first example I'm going to show is from this interval in the Pliocene, where we went from relatively warm early Pliocene conditions to more cooler and more variable late Pliocene conditions. And this study is from site 1165 from off the Fritz Bay margin. And the map on the top right is a survey of the hornblende 4039 ages around Antarctica with the color scheme legend here, pointing to the screen, legend here on the bottom right, showing younger ages in pinks, sort of the typical Ross Pan-African age in orange and red, and then older ages in the green, turquoise, and blue colors. And so you can see that there's a pattern of variability around Antarctica that allows us to have breadcrumbs for tracking icebergs. And the bottom right figure is a map, a model figure of the iceberg trajectories around Antarctica. The icebergs typically move counterclockwise with the countercurrent around Antarctica, and they basically spin out into the Antarctic circumpolar current, most dramatically in the embayment areas. And then on the left-hand side is the data from the Cook et al. Paper from 1165. The pie charts on the left represent the distribution of hornblende grained ages within these samples. And this is synthesized in this middle figure. The orange is the approximate modern distribution of hornblende ages, and the graph shows the variation in proportions of Wilkes Land versus Fritz Bay, local, distant versus close ice rafted detritus. And so you can see that that during the warm early Pliocene, that the distribution of provenance ages is very similar to today, but during the cooler and late and variable late Pliocene, the distribution of far traveled IRD from Wilkes Land becomes much more important. So process matters and the observations matter, and this plus other provenance stories and also far field evidence from sea level caused the ice sheet modelers to go back and think about what processes might have been left out that caused them to not be able to predict the level of change in the ice margin that was required to explain the geological observations. And so they added to their model mechanisms to account for ice cliff failure and hydrofracture. So the top left is the original model. B and C are with cliff failure and hydrofracture built in sort of to their model. And then D is with both of those mechanisms included in the model. And that's not the only thing. In addition to including those kinds of ice margin effects, Jackie Osterman did a study to look at the effect of dynamic topography, and the Wilkes Land margin was about 100 meters lower in the Pliocene compared to today. And if the reconstructions take into account those new mechanisms plus the dynamic topography, even more retreat on that Wilkes Land margin can be explained. Okay, so my group's goal is to try to pile on to the growing request to be able to examine the system from right next to the ice to the deep ocean. So we want to be able to go in and we want to look at the processes that are going on at and near the grounding line and beneath the shelf. We want to be able to look at both the geophysical imaging of the surface and the architecture of the sediment pile underneath the ice shelf, as well as out into the deep ocean. And to borrow from Mo Walczak, we need to take mud in order to be able to connect the modern observations and processes to the proxy evidence that we can gain from the ancient record. So one of the things that I think is kind of an exciting new development for International Ocean Discovery Program is adding X-ray capabilities onto the ship. So I think Expedition 379 was the first one that sailed X-rays on the ship, and now they've built a better system. And these pictures that I'm showing are from some images that Trevor Williams collected on the new instrument at IODP in College Station. On the left is a picture and then an X-ray of a core from the Amundsen Sea. And you can see the sort of density change with the lithology, but you can also see the black spots that represent the ice rafted detritus. The image in the middle is from a site off of Wilkes Land. I'm actually going to show some data from that in a second. And then the image on the right is a laminated section from the late Pliocene, early Pleistocene, from the Ross Sea margin, where you can see ice rafted detritus distributed through there. So the example that I'm going to show you from the Wilkes Land margin, site 1361, this is from a paper from Wilson et al. In 2018, and it follows a study of Cook et al. Looking at the late Pliocene that I'll show in a moment. Cook et al. As part of her study looked at the known distribution of geological terrains around the vicinity of Wilkes Land, and the red lines here are showing the sort of approximate sea level changes as a result of the ice moving in to these various places. And so by this survey of looking at the geology and looking at the isotope geochemistry from those terrains, this is neodymium isotopes against strontium isotopes. The samples that Karas measured from the interglacial times are shown here in the open symbols, and the more glacial times are shown here in the closed symbols. So you can see there's a significant change in the provenance. And then this follow-up study from Wilson et al. This is the neodymium isotopes in the red curve here. And this is the barium to aluminum as an indicator of a productivity below it. And for reference, here's the sea level and surface and subsurface temperatures from other coring sites, as well as this temperature from the Antarctic ice core. And you can see that every one of these times where Antarctica is warm, we get these significant differences in the provenance from these sediments. One provenance tool, and there's not a huge amount of these kinds of data available. But these are other two studies from around this region. This is the Pliocene study that originated this work from Cook et al. And then here's from a nearby core, 1356 is a neodymium record from the middle Miocene climate transition. Here's the core top from that. So it's similar to the other site. And you can see that for all of these, we've got this significant shifting provenance through there. I'd like to understand more about what that means. Is it related to subglacial meltwater? What does it mean about the extent of the ice margin at that time? So what changes in erosion and hydrology are expected with shifting ice sheets, and how will this affect biogeochemical cycles, biota, and hazards? In our group, Sean Gullick is going to show high resolution process information from geophysical imaging. Julia Wellner is going to be reading the sedimentary record, showing some examples of using proxies for temperature, nutrients, biological activity, and other things to understand the past changes around Antarctica. And John Hawkins is going to zoom in on the importance of understanding subglacial meltwater in the modern. And in general, to echo what has been said over and over here, an integrated approach is necessary. Modern processes form understanding of expressions left from the past. That's the proxy development. The past evidence provides a much greater ability to understand the full range of states. The historical observations are limited, and especially around Antarctica. Numerical simulations are essential, and observations are essential for guiding them. And Antarctica is a challenging place to work, but its role in global sea level and climate are critical knowledge.
Thank you, Sydney. We should now move on to our first 5-minute flash talks, the first of which will be given by Julia Wellner. Julia is an assistant professor at the University of Houston.
Hi, thank you, and thanks for that overview, Sid. You heard this morning that I might talk about Amundsen Sea drilling from the JR, and then just now Sid showed some x-rays from our crews there. I'm actually not planning on covering it, and the reason why is because we didn't make it into the ice-covered waters. The JR is not an ice-strengthened vessel really in any meaningful way, and it is not the answer to our questions or problems here. So what I am going to show instead is a few different cores that have been collected from the Palmer, each trying to make a different point. So starting with, as you heard today, there's efforts to get long ice core records. That's fantastic, but the marine sediment record is always going to be longer than the terrestrial record. Whether you're looking at ice cores or sediments, we're always going to be able to get more from the sedimentary record. The example shown here is from the Northwestern Weddell Sea, and it goes from the Eocene to the Pliocene in snapshots. It's not a continuous core. And on the left side of the core figure, we have sedimentology that is showing that we were able to identify tidewater glaciation by the late Eocene in the Antarctic Peninsula. And then on the right side of the figure is all new data from Emily Tibbett that's just been published because these cores have been well preserved now at Oregon State. They still allow modern analysis. And in this case, she's used biomarkers to look at both air and water temperature. And so using these three records from the stratigraphy to the air temperature from soil markers through the sea surface temperature, we're able to reconstruct the different timing of how these things happened. Glacial onset, then air cooling, then ocean cooling, coincident with more global ocean, deep ocean cooling. So the photo on the left of the screen is from the program called Shall Drill. That is the Nathaniel Palmer with a rotary drill rig over the moon pool. The moon pool was cut in the Palmer, for those of you that don't know, in 2004. So 12 years after the vessel was launched, the moon pool was cut in order to facilitate this style of drilling. It worked. We haven't repeated it beyond the 2 legs that it did, but don't worry, I'm not proposing a large moon pool a la the Sir David Attenborough or similar vessels. Rather, I'm trying to show you that sometimes smaller scale solutions creatively applied can allow the collection of the data needed. So in this case, modification and acquisition of this core. Next slide, please. So another type of coring that is done on the Palmer is piston coring, gravity coring, casting coring. So I'm putting these all in my medium cores that allow access to the deglaciated ice bed. It's hard to get through the ice. It's a lot easier to go get all of these cores from the shelf, and they still allow us to reconstruct past glacial conditions. The figure from Totten et al. Just shows an assemblage of the many cores we collected around the peninsula, allowing regional temperature and deglacial records. I only have 3 slides, but 4 points. So the second one on this slide is that the paleo record sometimes shows us things we've never observed. In the case of the Graham et al. Paper, which was from the Thwaites embayment, the paleo record shows us that the ice has retreated faster than we've ever seen it. And going out and getting these shelf records is the only way we're ever going to know that. And so for my final slide, I'd like to show you some of our newest cores. These are from the Thwaites Glacier area as part of the ITGC and Thor project. And so the final type of core we take is a multi-core or mega core. They're not extra large, rather they are collected in groups of high resolution coring that preserves the bottom water and the very upper part of the sediment, allowing us to reconstruct very recent change. So in the long core description, what you see there in a figure that's in second review now in PNAS, is the core photo, the X-ray down the middle, and then the CAT scans on the right. So X-rays are great, CAT scans are even better. And at the top of that core, we have a lead-210 profile, allowing us to reconstruct the past 100 years or so. And in the big blue bars, I want to draw your attention to work that is being done right now by Frankie Pavia, who's looking at the flux of helium-3 or interplanetary dust particles that are coming into the Amundsen embayment. And the red line at the base of the plot there is calculated how much flux of helium-3 or interplanetary dust should there be just from the known melting. The blue bars are what we actually get in the core, suggesting there's a lot more meltwater than observed from calculated melt, and shows our ability to use cores to know what's happening now. Thank you.
Thank you, Julia. We will save our questions for the end, so please enter them in Slido as we go along. Our next flash talk is by John Hawkins. John is an assistant professor at the University of Pennsylvania.
Thank you very much. I hope my bills work, otherwise it's going to be quite embarrassing. But thank you very much for inviting me to present today, despite the fact that I'm going to whisper this. I've never been to Antarctica, but I'm going to do my best to hopefully represent some of the research that's been done down there, and I've been lucky enough to have some samples delivered to me to analyze. So I'm going to start my story by talking about liquid water underneath the Antarctic ice sheet. And this has kind of been talked about a little bit in the past day or so, but I just want to start by showing you that there is liquid water underneath the Antarctic ice sheet. We've known this for quite a number of years now, going back decades. The most recent estimates of subglacial lakes that might exist underneath the Antarctic ice sheet is about 670 subglacial lakes. The blue triangles on this figure at the top here of the Antarctic continent show active subglacial lakes, and these are subglacial lakes that we know drain and fill on cycles. And these lakes are thought to be connected to the continental margins and are likely to deliver fresh water to these marginal environments. The lower figure there is from a recent paper by Christina Dow, demonstrating that subglacial channels are likely to persist up to 500 kilometers into the Antarctic ice sheet margin, delivering water from the interior of the Antarctic ice sheet to coastal environments in Antarctica. There's an even more interesting story here, and this has just really emerged in the past year or so. Some great work that's been done by Chloe Gustafsson that was published in Science last year, demonstrating that a deep groundwater system likely exists underneath Antarctica as well. So that subglacial lake or kind of ice bedrock interface environment that has liquid water isn't the only place where there's liquid water underneath Antarctica. There's a subglacial groundwater system as well that could likely persist up to 1 kilometer in parts of West Antarctica. And it's likely this groundwater system exchanges water with this overlying freshwater subglacial hydrological system, and therefore exchanges things like nutrients and carbon. That's my bill going to work. Okay, so there is some kind of exchange between this subglacial and this groundwater system. This matters because of biogeochemical cycling, where there's water, there's life, where there's water and sediments, there's subglacial geochemical weathering. Actually, Colleen Hoffman and Patricia Yeager did a really nice job of presenting why iron is important for the Southern Ocean. It's a limiting micronutrient in the euphosic zone of the Southern Ocean. And that's partly what motivates us to study subglacial environments in Antarctica and their importance potentially in delivering freshwaters to the ice margin, the marine environment. And there's been a whole raft of really neat research that's been done over the last decade or so, showing active subglacial biogeochemical cycling in these environments, both hypothesized or modeled, but also measurements from subglacial lake environments, and also measurements from the dry valleys in Antarctica. These are just a small example of the kinds of studies that have been done. And some of these studies are indicating that subglacial waters that might be delivered to the marginal environments and into the marine environment could be enriched with things like iron. This is the only data I'm going to show you in this short talk. This is some data from a publication that we put out a couple of years ago, and I've highlighted iron there. This is concentrations of these elements relative to the global riverine mean. In Mercer subglacial lake, where these samples came from, there's really, really high concentrations of filterable iron, up to 10 micromolar of filterable iron, sometimes higher in some of the samples that we have. And this water is kind of slightly turbid. This is the water after a year of just sitting. It's got really high colloidal particle concentrations, and a lot of these colloidal particles carry some of these important micronutrients that could be important in some of these coastal marine systems. But the only information we have on these subglacial waters in terms of their geochemistry, or direct access anyway, is from just 2 subglacial lakes that have been drilled into in this part of Antarctica, just upstream of the Ross Ice Shelf, and a host of studies that have been done in the Antarctic dry valleys. So we're really limited in terms of spatial extent of subglacial meltwater end member samples that we have. So being a non-oceanographer and someone who is possibly unlikely to use this new research vessel, I thought, well, what could be the benefit to my kind of research and my community's research? And I spoke to some of my chemical oceanography colleagues who are interested in some similar kinds of questions. And these are just some of the ideas that I had that for discussion later. So I think proximity to the ice front, a lot of other people have talked about this, getting towards the ice front. If we're going to try and sample submarine groundwaters that are coming from underneath the ice sheet or subglacial discharge, we need to get as close to the ice front as we can. Obviously, leading edge science capabilities. I put in here things like trace metal clean facilities. I know the David Attenborough, for example, now has a dedicated clean room for doing trace metal work, and I'm not sure if that's a possibility or not for the new ARV. And from a selfish perspective, subglacial research, trying to look at questions like how much water is there that's being discharged from underneath the Antarctic ice sheet? Where is it flowing to? How far out into the ocean is it getting? Its residence time and therefore its geochemical signature. All important questions that I think need answering. And the overarching theme to this really is the biogeochemical importance of subglacial water. Is it important in terms of connectivity between freshwater and seawater? And also, can we contextualize modern observations in terms of past signals as well, using some of my colleagues' paleo archive data? And on that, I'm sorry, I've run slightly over, but thank you.
Thank you, John. Our next speaker is Sean Gulick. Sean is a research professor at the Institute of Geophysics, associate chair in the Department of Geological Sciences, and co-chair of the Center for Planetary Systems Habitability at the University of Texas at Austin.
Great, thanks very much. So my role here is to talk about subsurface imaging, basically around Antarctica, and I'm going to do this sort of from the distal to the proximal. So the map here on the top left, all the white lines are existing seismic lines of all different qualities and penetrations. And often we have a pretty good record of the distal part of this. So this is just an example, for instance, off the Amundsen Sea that you see in the bottom left here that shows this transition from a pre-glacial world to the transitional into a full glacial. And many of our best distal records, like Sid talked about, for instance, come from drift deposits, such as the one here shown off Wilkes Land, where there's these wonderful ice rafted debris and this chance to look at the proxies that we can see. But the next level of this is to both have additional subsurface imaging. So we have the ability to do things like look at this volumetrically, not just in individual single locations. So this example here in the top right off of Fritz Bay is a really good example of that, where if there's dense enough seismic coverage, or even in the future, maybe 3D seismic coverage, you can create maps or isopac maps of volumes of sediments that have come off of given conduits or given subglacial basin regions of Antarctica, and be able to look at the history of the ice and ocean and sediment interactions in the form of their final deposits into the marine environment. And then proxies within these can inform us about changes of the environment through time. So, that's just an important argument, I think, for continuing the capability on the new ARV to have the ability to collect seismic data and to then tie these sequences into coring and ocean drilling of one form or another to understand the record. And next slide, please. Unless I can do it. Oh, I can do it. Good. Okay. And then as we move a little bit closer, one of the challenges that has been true since people have been trying to image the area around Antarctica is that in many cases, the shelf to slope to deep sea transitions are very difficult to map across. And here's a good example from the Bellinghausen Sea on the top left, where just the nature of how shallow it gets at the shelf edge results in multiples getting in the way of mapping the stratigraphy, and just the slope sequences being thinner in several cases make it very difficult to make sure that the stratigraphy and the ages that we have of the deep sea can be accurately mapped into the shelf. It's pretty doable places like the Ross Sea, but there's a number of locations where either we simply don't have the data that cross the shelf edge, or the data has challenges to it due to just the geometry of the situation. And so, the importance of linking the proximal records to the distal record is hard to overstate. I think the solution in this that is something that's being explored now is increasing use of AUV technology, such as this really great example from Ali Graham that was, a multi-beam bathymetry study to study the proximal edges of the shelf. But we need to have the ability to potentially think about also doing subsurface imaging with these kind of capabilities, which requires greater power and requires us thinking about things like an A-frame with enough oomph to be able to deploy the larger towed or autonomous vehicles, such as just sort of this example down here from the right, which is a currently being studied possibility of a deep towed seismic vehicle that might be able to be used in a place like Antarctica. And then next slide. So this is then moving into the proximal record. And here we have had great successes when we can get into polynyas, we can break through the ice and then deploy data within those kinds of environments. And so this is an example from the Totten system on the Sabrina coast of East Antarctica, where we can actually see those transitions. Again, this MS1 to MS2 is this transition from a pre-glacial to a transitional glacial environment with things like tunnel valleys, such as this example image from the North Sea from Julian Dowdswell in the bottom right, that represent a very meltwater rich kind of glacial environment and links to thinking about things like the subglacial water systems that we just heard about, and then a transition up to the sort of modern polar systems. But to understand this evolution through time of these different types of glacial systems and what's driving this ice ocean and ice sediment interactions is going to require sampling. And if we think about it just from a standpoint of what type of sampling we can do, the little red dots on here represent what piston coring can do. The yellow is then what happens if we get the jumbo piston coring kind of capabilities. And then the green represents what happens if we can get something like the MEVO 200 to be launched by our new ARV to be able to get these 200-meter sort of penetrations and actually have a chance to really understand this kind of record. So, what is needed again is, the capability to do the seismic and multi-beam and so on, but also the capability to think about seabed or icebreaker-based drilling systems to really get into these proximal records and then tie it back into the deep sea. Thanks for your attention.
Okay, thank you, Sean. We now have 10 minutes for questions, 10-ish minutes for questions. If there's anyone in the audience who has one or any in Slido.
We have one from Slido.
Oh, you do?
Yep, and then if you have a question. This one's for Julia. You talked about a coring technique that was best conducted through a moon pool that was cut retroactively into the hull of the NBP. Will the lack of a moon pool negatively influence the kind of research you and others in your field might conduct in the future?
Potentially, yes. There are multiple ways to achieve that length of coring. And Sean, in fact, just mentioned that there is a system called a MEBO 200, which is a seafloor drilling rig. There are also over-the-side drill systems. So if we consider there to be a combined 3 different styles of how we might achieve long rotary core drilling from an icebreaker. One is on the seafloor, one is over the side, and one is through a moon pool. The only one that's, achieved some level of success actually through the U.S. Antarctic program so far is Shaldrill. It had 2 cruises in 2005 and 2006. Again, immediately after the moon pool. It worked, it would work again. Over the side system, it looks promising in many ways and might be a good solution, but there's a lot of unknowns about how it will operate in different sea states, for example. And then the MEBO systems, the seafloor systems, I see 2 significant drawbacks to those. I've not used one personally, but they have proven only moderately successful in drilling through glacial sediments. They have problems with overcompacted sediments. They have problem with cobbles and ice rafted debris, and really struggle to achieve records there. And then the second problem with Amoeba, which may be overcome since my information has dated, is that the umbilical on MEBO systems is quite sensitive and it might not function well in a ship that's moving around to avoid ice. So I would say the Shaldrill style is maybe a known, reliable, not perfect, but possible system. Thank you, Julia.
Okay, my question is for John, and it kind of mirrors Andy's question, but I was wondering what specific observations along coastal margins or key measurements might help you elucidate subglacial processes? And I'm thinking like beyond iron measurements, like seepage meters or other parameters that might require development, like sensor development or something like that.
Well, that's a really good question. I kind of threw right in at the end something about novel biogeochemical sensors, or I might have mentioned sensors. But there's, in develop, there are biogeochemical sensors that are that might be able to perform kind of autonomous measurements of things like iron underneath ice shelves and potentially up to the grounding line. And we've heard some great talks over the last couple of days demonstrating the power of these autonomous vehicles to get close to the grounding line. And I think that's a really great way of potentially getting at some of these subglacial meltwater inputs directly. I'm sure there's also other geochemical traces that could be used, like noble gases, for example. Certain isotopic traces as well that could be used to trace subglacial meltwater inputs. So I think it's just combining all those different things. But I think autonomous vehicles with novel biogeochemical sensors in the future, thinking 10, 20 years down the line, could be one way of taking some interesting measurements very close to the grounding zone where we expect some of these waters to be coming out.
Great, thank you. Matt, do you have a question?
Yeah. Sean, can you hear me? There's a question for Sean.
Yes, I can.
Cool. Sean, are there any other towed geophysical instruments that we should be thinking about for the ARV that would be complementary to great towed seismic? I'm thinking things like controlled source EM, any other geophysical tools, and what sort of requirements would that have?
Yeah, that's a really great question. I think controlled source electromagnetic methods
Sean,
are
muted.
better.
Okay, good to go.
Okay, great. Yeah, I think controlled source
No,
electromagnetic.
sorry.
No. How about now? Yeah, you guys can, the Zoom
There you
can
go.
hear.
Now we're good.
Okay, great. Yeah, I think controlled source electromagnetic methods would be a great option. It requires a reasonably sized A-frame and power capabilities. to be able to tow the larger sources and receiver systems for those. But you could envision that would actually have the ability to potentially directly sense the freshwater connection or the seawater freshwater interface in the subsurface on the shelf edges. And as you approach ice margins, I think that would be pretty exciting. And you could conceivably also do that with an AUV component as well. So that's something to think about. And then, there's also an opportunity there to pair that with, marine, with drilling as well, whether it's a MEBO system or an over-the-side system. Those are something I think we should be thinking about, that there's this, not just the stratigraphy, but we have the ability to think about where the water is and can we actually sample directly into those systems for biogeochemical reasons.
Thank you, Sean.
Yep.
Okay. All right, so we need to move on, but we'll hold your questions in Slido and you can approach our panel afterwards. So I'd like to thank our panel for their great talks. And this finishes our last session for today. And we will move into breakout rooms. Similar to yesterday, we will be using that group process of establishing both science priorities and essential capabilities called the KJ technique. This method uses the sticky notes we worked with yesterday, virtual and physical, to kind of facilitate our discussion. We'll spend the first 30 minutes in each session brainstorming and the second discussing techniques. So first, please decide if you would like to participate in a breakout room session that you see on the screen behind us on global climate and ocean circulation, which is related to our first session today. Or if you would like to participate in a breakout room session on biota and ecosystems, which is related to our second session, or if you would like to participate in a session on shifting ice sheet and changes in erosion and biogeochemistry related to this session. Once you have identified the session you are interested in, please go to the room indicated on the slide behind us. And if you find the room full, like yesterday, feel free to migrate to another room. Yeah, is there a question there? I don't know. If you are a moderator, facilitator, or rapporteur, you should report to your assigned room, which is shown here. A reminder that the rapporteur will be reporting back at the end of this for a full group discussion. So please take notes. Thank you. Round of applause. Those are great.
Yeah, all the rapporteurs, come on up. And I don't know how many sessions combined. How many rapporteurs? Hi, Sid. Just 3? Okay. All right.
And we're sharing.
With same session.
Yeah, so maybe it's just 2.
Oh, we have one online, don't we?
Oh, yeah, maybe so.
The rapporteur for the in-person climate and circulation, whoever's doing that, could please come up to the stage. I'm not sure which
Sharon,
version.
Sharon,
Is it Sharon? Okay.
are you here, Sharon?
He's getting, yeah.
And do we have, are we online too? One online, okay. And I see Gulick here also. Do we not have that one? Sean.
Right, I'm here.
Oh, you're online? Okay, thanks, Sean.
Yep.
Whichever, from there, either or.
Yeah.
Oh, we're waiting for a slide.
Yeah, would it be possible to get Mo's capabilities? Mo.
Oh, capabilities. Should we do it one of the other ones first then, if we're waiting for a slide?
Sure.
Can we jump?
We'll do
order?
the virtual climate and circulation first.
And this one's Alex?
Yeah, I'm here.
Okay.
I cannot see the slides though.
I don't think we can see you either. Okay, we see the slide. Alex, can you see it?
Yeah, I can see it.
Okay,
Yes.
great. Go for it.
Okay. Yeah, we had a small but very intense discussion and a very good discussion, I think, among this online group. And I think in terms of science priorities, while we all have things we are interested and excited about, we all agreed that the very top 2 science priorities are to really get at the CO2 budget, the sources, the sinks, and how it responds to climate change, and to really understand ice shelf ocean interactions. And these are things that I think are certainly important on a level that goes beyond all our interests and is important to society as a whole, and the future of society on this planet, and if and how we can live on this planet. So I think that this is really pressing priority, and that came out very clearly in our discussion. 3 and 4 are transport processes and sea ice, and we thought that these are the processes basically behind these 2 priorities. So how the ocean circulation modifies these components or these priorities, how it leads to interaction between the shelf and the open ocean, how deep convection works, and how upwelling and stratification, how to understand upwelling and stratification processes, basically, that are all processes that lead to this, to the understanding of this first 2 priorities. And the sea ice is basically, we thought would be an indicator, a very good indicator of the changes that are ongoing, that we can observe and have to understand how it varies in order to also understand the top 2 priorities. And it's, I think I would like to add, it's not just an indicator, but it can also really affect the ocean and modify it. So yes, I think that was our summary of the science discussions. In terms of capabilities, the 3 key capabilities that I think we need to answer these questions is, first of all, to have the access to the ice-covered region. And I think that came out throughout these 2 days and that the ARV needs to be the vessel to do that. And capability number 2 is to really extend the range of the vessel while it's going into the ice, to be able to observe larger temporal and spatial scales around the ship, including going under ice shelves, for example, going under sea ice, going deep in the ocean, going further away from the ship, and coming back and having the capability of deploy the instruments from the ship. 3 is a capability that we basically need to get at these budgets, I think. We need a network throughout the Southern Ocean of different technologies, new technologies, existing technologies, tools or platforms that provide observations that are independent of the ships and that we can use to understand and monitor the wider changes of the Southern Ocean. And we really need the ship to get to these places and deploy some of these tools, but also to maintain them. And something that also came out that through something that goes through all of this, be it science priorities or capabilities, is international coordination. We cannot, as a Southern Ocean or Antarctic community, I think we cannot just care about our own sector of the Southern Ocean and do science there or do surveys in this sector, but we have to coordinate. We have to build arrays and sections that are useful to understand the overall budget and to help each other to maintain this network that we were talking about. And also coordinate in terms of variables that we measure, for example. So I think that's most of what we have talked about as a summary.
Okay, I see international coordination down there at the bottom. Is that what you were talking about at the end?
Yes,
Yeah.
so that's there at the bottom, and we put it at the bottom because we think it goes over all of it. And maybe one thing to add to this is that we think it should go through existing international networks like SCAR or SUS that are in place to help with this, and that we have to leverage these.
Great, thanks. Okay, we'll jump over to Sharon Stammerjohn for the local session on the same topic.
What Alex said. So it's good to see that we pretty much came to the same priorities and capabilities. We may have ordered them a little differently in the sense that we actually just went ahead and grouped everything under everything. So the first one, understanding ice-ocean interactions, for example, heat exchange and cryospheric ocean impacts. So here we're talking about all ice, from glacial ice to sea ice. So it kind of encompasses what Alex just showed, I think, for really his 1 through 4, but 3 and 4 that added to the CO2 and the ice shelf ocean interaction. So it's hard. I mean, it's going to be very difficult to kind of express our discussion that we just had, because you can imagine it was in a lot of different places. And basically, one way to summarize that is we kind of want to look at the whole system. And we felt that it was important, or I kind of offered this up. So please, anyone in my group chime in, but you really want to focus on the processes when we're talking about these priorities, because then that gets to the question of what capabilities are needed to address that, right? So that was number 1. Number 2, understanding sources and sinks of greenhouse gases and the role of the Southern Ocean. So similar to what Alex proposed for the first priority, there was also a bit of discussion, and this ended up going into priority 3, I think, but really, what is the ocean's role, the Southern Ocean's role in the global climate system as well? So it's not only understanding how the Southern Ocean is responding, how the sources and sinks of greenhouse gases are changing and actually modifying the Southern Ocean, but then the role of the Southern Ocean in impacting global climate. So hence 3, understanding how changes in Southern Ocean circulation and mixing regulate the global heat budget. So those are our three priorities, pretty broad and very multidisciplinary, I think. So getting to the capabilities. So we have development and support for remote and autonomous platforms, instrumentation for measurement of water column and sub-ice shelf processes. So although this says, so we have water column and sub-ice shelf processes. So we're looking at, again, that whole, we talked about spatial domains and temporal domains, but we're really talking about all the way from, the Antarctic ice sheet to the open ocean. And so how can we develop capabilities so that we can support observations that cover that kind of spatial domain? And we also need year-round access, right? But so in this particular instance, though, remote and autonomous platforms and water column and sub-ice shelf processes, that's all has to be ship-based enabled, right? In order to deploy those platforms, calibrate those platforms. And so the second capability, access to the coast and the ice shelf, sub-ice shelf, coastal areas, and that includes, of course, getting off the ship and onto the coastal areas. So some kind of air support likely that would involve. Again, and that's all part of the science priority 1 and 2, really. Ability to conduct year-round monitoring. And so this was kind of interesting because the ability to conduct year-round monitoring, that can include really 1 and 2, right? It can include this autonomous remote platforms and ship-based platforms. So it also can encompass cyber infrastructure, international multi-agency. So it's a big kind of bucket, really. And then lastly, overboarding capabilities for heavy equipment, including but not limited to moorings, geophysical, and coring, et cetera, which is probably our more specific capability. So I feel like I'm not doing our group's discussion justice, and I would offer any additional comments. Looks like we have some time, if anybody wants to offer. I think we can agree that what Alex had outlined was very similar to our priorities and capabilities.
Okay, thank you. So we'll move on to the ecosystem group, and it looks like that's Allison. Did you have a merged group also? You're reporting for both, or is it just one? Yeah.
I think that there was one online.
Yes. Yes, David, sir. But we have one listed here with Eileen too, but those two merged. Okay.
Okay. Heather did a great job at moderating our session.
Sorry, David, we're going to start with Allison.
Oh, okay, bye.
Sorry, David. You can beat me up later. So the science priorities that we had a pretty small group here with lots of thinking. We got to, it was a good brainstorming session. And I don't think that these are particularly ranked. I think that they're quite evenly ranked. The first, though, is ecosystem structure, function, and biochemical linkages. This had the most stickies associated with it because it really is understanding the ocean as how the environment and organisms are functioning together. And so there was a lot of different ideas all under this kind of ecosystem bullet item. The next one is adaptation, resilience, and evolution, with a lot of the ideas that I talked about earlier today. But in order to really understand what is happening, how Antarctic organisms, how they're built in terms of their physiological resilience to withstand change, and even to understand some of the really basic properties of how they exist in really high oxygen, supersaturated surface waters and high UV. there's a lot of really specific Southern Ocean features that biota have adapted, and being able to understand this beyond maybe a few model taxa is, I think, important, as is understanding the evolution of life. We have a poor understanding of even how many organisms are endemic to the Antarctic. The third item is biodiversity and marine protected areas, and all of the science that is related really to support Antarctic conservation. This is a big thematic area under SCAR today, but we are knowledgeable about a small amount of the biodiversity in Antarctica, and the vast amount of it holds lots of barriers to understanding, a lot of it due to access, a lot of it due to our fact that we're normally there in summer. And let's see, I think it changed.
We had a slide glitch. There it is.
Thank you. And for capabilities, our first set of capabilities were all sort of under the umbrella of access to the nearshore, and what hasn't, similar ideas of what have been said in other groups, but also to the deep sea. And the deep sea environments are widely undersampled in Antarctica. There are a lot of unique habitats, seamounts, hydrothermal vents, cold seeps, the under ice regions, under ice shelves that are really interesting from a biological perspective. And I think there was a big theme about having sampling access over the annual cycle and in winter specifically. Developing sensors and sampling instruments and support systems, sensors for biochemistry, biogeochemistry, having clean rooms, potentially genome sequencing. There's really small little genome sequencers you can stick in your briefcase. ROVs, helicopters, maybe even a submersible, or at least a ship that could host a submersible. Large volume water samplers, modern net systems for catching but not destroying the plankton you're trying to sample. There's modern systems for doing in situ cell imaging, biooptical sensors, zooplankton collection. We talked about the need for computational and IT needs, both at sea as well as on land. Having broadband access and potentially a high performance cluster on the ship for doing modeling, and if we're doing genome sequencing, for doing processing of the data. We talked about teamwork and collaboration and really how important this is on the ship, and having pre-planning meetings, training highly functional integrated teams to go to sea, partnering and establishing, maybe facilitating international partnerships, both bringing international participants with us, but also us going to sailing with other countries. We asked the question, is 60 days at sea enough? For most of the needs that we had, we think so. And we also discussed a little bit of the idea of how the ship is going to work in the sort of ship planning. When you have this large ship that can have 55 berths, what happens when you have small teams, and how do you best organize the use of the ship with small research teams and them working together, if they're together, or however that works. Is there anything else that I left out from people in our group?
Great, thanks, Allison. Okay, David, if you're still there, you had the virtual session on ecosystems. David Ainley.
Is there another set? Oh, okay.
You see the slide?
Okay, so we had a relatively small group. We talked about integrative studies to better understand midwater food webs, as well as the connection between the midwater food web and the benthos. I want to say that we're talking here about high latitude coastal ecosystem, which is dominated by continental shelves and slopes. And in this world, polynyas are biological hotspots. But anyway, there's been a lot of work on, upper trophic level creatures, and there's also been appreciable work, at least in the Ross Sea, on the assessment of the species composition of benthic communities. But there hasn't been yet any integration of the two. So that seems to be one priority. I think work at McMurdo Sound and particularly Prairie Lab has been a hallmark of work on physiology and adaptation of Antarctic organisms, as well as the genetic aspects of these adaptations. And McMurdo, is the place. In the western McMurdo Sound, there's an oligotrophic ocean because the water there comes out from under the McMurdo ice shelf, and it's as quote unquote gin clear. There's nothing in it. So it is an oligotrophic system, totally different from the eastern Sound where the water flows in from the Ross Sea and it's like pea soup. And so the community in the eastern Sound is like totally contrast to the western Sound. And so this offers an amazing chance to compare these two sorts of systems and so working with organisms to how they cope with these two different types of systems would be a way to continue to go. And this sort of leads into biodiversity of organisms. Again, the Ross Sea is rich in critters. There's like 400 species were first described in the Ross Sea, but I really don't know how far along gotten in terms of their genetic signatures. But certainly this is an area where there's much potential. Those are science priorities. Well, I should say, there's a lot of work at Palmer Station, and it's really elegant work that's happened there. But the Palmer Station system is not anywhere comparable to the southern Ross Sea continental shelf system. And so complementary work could continue in both areas. And that's really the contrast is really instructive. Okay, so in terms of capabilities, I've at least made the case that the McMurdo Sound Fast Ice is an incredible platform for conducting science. The group talked about having small boat access, but I believe that mostly applies to Palmer Station. Over the years, every once in a while, someone suggests there could be some small boat work in McMurdo Sound, but I don't know that logistics and safety considerations maybe put a quash on that sort of thing. But further work with at least the small boats over at Palmer could well enhance the science that goes on there. In McMurdo Sound, there's incredible access to creatures. from the fast ice. And there is a well outfitted aquarium system at Prairie Lab. And so there has been some work on, using live animals and looking at how they adapt to changed ocean, like a warmer water versus colder water. There has been some work at Palmer Station in the aquaria there, but that system is not as well outfitted as the system at Prairie, and so some work could be done there to improve the aquarium systems at Palmer. That sort of gets into the third attribute here, which pretty much I covered. McMurdo system has been underutilized over the last 10 years or so for reasons beyond my pay grade. As I said, the aquaria at Palmer apparently need some work to make them more amenable to additional or further or continued research. I think I covered what we covered. So thank you.
Great. Thanks, David. Okay, we'll move on to one of the sessions on erosion that met in room 120. So that rapporteur is Sydney Hemming.
I think it's.
Oh, or are you going to tag team it? Oh, you combine.
Yeah.
Okay. We got a tag team with John Hawking. So let the mud wrestling begin. You want me to start? Yeah.
The one that's up is actually the virtual one.
Yeah, Sean, you did run the virtual session, Sean?
Yeah, and that's,
Yeah, okay.
there we go.
We'll
Do that one
get to
first.
you in a minute.
Oh.
Thanks.
Yep.
So there were two of us.
Okay, perfect. So our three science priorities were are kind of interlinked and kind of go hand in hand with each other. I think in no particular order, really, apart from the number of votes that they got each. But when we had a discussion, they kind of all came out around a similar kind of priority level. The first is current sediment delivery processes and provenance. So where the sediment is coming from today, so it's contemporary processes, what is its composition, erosion rates underneath the ice. Then we're going on to
Past ice and paleoclimate, how much, how fast, and that's basically taking the knowledge that we gain from the process studies for current sediment delivery and the proxies that are developed as a result, and connecting that to coring records of the sediments offshore.
again, helping to feed into that is the provenance of the sediment that we thought were priority for contemporary processes. Then the final one we have is subglacial, and we kind of group that into groundwater, freshwater, fluxes, and terrestrial hydrology. So that's really about subglacial meltwater flux from the ice to ocean, again, contemporary based, with a terrestrial hydrology focus. How much water is there? What is its composition? Where is it coming out? It's really important for things like stratification, but also coastal chemical composition, and also a number of physical processes are strongly tied to the amount of meltwater coming out subglacially, such as circulation underneath the ice shelf melt. And again, that tying back into informing us about past ice and paleoclimate as well. And then onto capabilities.
Yep. High priority for capabilities is being able to do drilling and coring. And that's basically so that we can obtain sedimentary records near the ice, on the shelf, and even offshore, and get long and continuous records. We want to be able to look at the processes and the timescales of processes.
I think as well, because this keeps on coming up amongst both days and a lot of different groups. Amy Leventa would mention that there's kind of a strong need for a workshop, particularly on drilling processes and options in the future that should involve both scientists and engineers, and an international cohort for that as well. And I believe the design team has been talking to the OSU core repository for that to figure out kind of drilling options into the future. The second one is, again, has come up quite a number of times, but that's AUV, ROV, stroke drone support. And we talked about making sure that deployment, recovery, and tracking infrastructure is incorporated into the vessel, which I'm sure it will be. But also things like deck space and electronics. There's going to be a lot of deck space on the vessel already, which is great. But making sure the electronics are, state of the art and able to tie in quite closely with deploying these kinds of vessels. And we also talked about potential sampling and sensing capabilities for these drones. So remote sampling of water and sediment underneath the ice shelf in particular, and getting close to the grounding line, as close to the grounding line as possible. And also incorporating next generation sensing, both kind of funding to support the development of next generation sensing, so biogeochemical sensors, which again came up in one of the previous discussions.
And shipboard geophysics, and also that's basically to connect the dots between the modern processes that are going on and the sort of preparation for exploring with the sediment cores as well. So we think that the ship ought to have capability for doing surveys with seismic, and we also think that it should support geophysical measurements from the any AUV, ROV capabilities.
And the final thing that we discussed in terms of capabilities is that we knew that the new research vessel would be a Class 3 icebreaker, which is great, but it was brought up a couple of times that station keeping is very important, particularly for facilitating some of the drilling capabilities that we thought would be really important in terms of the science priorities.
And just in general, it was brought up and we all agreed that having sustained support for the engineering and design modeling ability to support the ROVs and AUVs and communications would be really important to keep in mind.
I hope we hit all the key pointers, but if anyone else in the group has anything else they want to mention.
Great. Okay, thank you. We'll move on to hear from the virtual session on erosion that has Rapporteur Sean Gulick out in the
Great,
ether.
thanks. Can you hear me?
Yeah.
Great.
I
The
think
other
you might not
slide.
have your slide yet.
No, it was just
There it
there. There it is. Perfect. Okay, so we had a small but very engaged group and kind of fairly quickly narrowed in on some really key science priorities under these topics. Primarily was, or number one was mapping and characterizing the eroded products from the glacial systems. And so that's on sort of all scales and both time and space, so both proximal and to the distal record. We also then had a key priority in the world of meltwater fluxes. So understanding meltwater fluxes, their properties, the pathways in the marine environment, both at the seabed, but also being able to characterize what's happening under the ice shelves. And then both of these things, understanding the sedimentary record and understanding meltwater, kind of feed into the effort that's required in modeling glacial dynamics and ice sediment interactions. That's probably really critical to understanding the whole system. Just not directly a capability required for the ship, but from a science perspective, it's really important that those communities continue to talk. Some areas that we didn't spend as much time on, partly just to who was in the room, were the hazard side. We mentioned the hazards of large icebergs, hazards of submarine failures, but just mentioned them. Also talked about the need to probably better understand the solid ice flux process and even the mechanism of delivery of ice rafted debris, since that's one of our proxies once we get to the deep sea. In terms of capabilities, had also a lot of agreement. We kind of tried to group them a little bit. So one is, the ship-based observational capabilities, all the things you would expect, the CTDs, multi-beam systems, sub-bottom profilers like chirps, ADCPs, and long goring systems that would be part of the ship facilities, but then also the ship's capability to deploy key systems such as seismic reflection systems, controlled source electromagnetics, drilling systems such as the MEBO, or if there was an over-the-side possibility, AUVs, and then even the possibility of thinking about small vessels where the ship could be a mothership, not just for AUVs or ROVs, but also potentially for small vessels that could go in and do either on ice teams or proximal sampling. So sort of thinking about this as a bit more flexible space where it can be kind of a mothership, if you will, both for AUVs and for crewed operations. And then all of these require, the obvious things, enough deck space for things like the AUV vans, for the seismic systems, or if the compressors are not built into the hull, then you need space for those. And then bunk space, because a lot of these kinds of systems require a lot of technical support in addition to the science support. And then storage, if we're going to do quite a bit of coring or quite a bit of, drilling related activities, you need space to put the cores. So that's a really key constraint, I think. And then looking out into the future, future technological developments are really needed in this world of AUV, especially for AUV-based imaging and sampling in these kind of environments. But then also, if you ever did not a seabed drill, but a over-the-side drill, then we would need to think about automatic heave compensation as a technological development in that setting. And I completely concur with the comment about potentially a workshop in this area of the best way to do drilling in the Antarctic would be excellent. And I think if I missed anything, hopefully the group will chime in. Thanks.
Great. Thanks, Sean. Okay, thanks to all of our rapporteurs and everyone who participated in the breakouts. We are going to have a 15-minute break now, but stick around. There's more, and we did change up the afternoon integrated discussion a little bit. So I'm going to pass to Caroline here, who will explain that to everyone.
All right. For the last breakout, we're going to have one in-person breakout room, and that's going to be in the lecture hall. We will, as Alan said, have a break. So here it's 3:15. We'll please be in the lecture room at 3:30. We'll come back here following, we'll have our breakout room until 4:15 and then come back and we'll do the last report outs.
And there's a virtual version as well, run from room 114.
And just one thought as you're going into the break and into the breakout rooms, we're going to have the discussion kind of around looking at all of the different capabilities that came out of the other session rooms. All right, ready, break.
Science Foundation. So we really value everybody's diligence and input and thoughtful responses over the last couple of days, and can't thank you enough for all of your help. The science talks were just phenomenal, as was the discussion. So I greatly appreciate it on behalf of the committee. Second, thank you to NSF for showing up and supporting and answering lots of questions and being there to help us through our thought process so we can get the best report that's the most impactful for what they would like to achieve. And then lastly, just a final thank you to all of the staff from the National Academies for just a phenomenal job. Margot, Miles, Caroline, everybody who supported it, the breakout sessions. This just went so smoothly, so I can't thank you all enough. Okay, so rapporteurs, or really rapporteur, could you please come and sit at the table? And I don't know, did the virtual have an in-person rapporteur? Okay. So both of you.
Or online.
Oh, online. Okay, so we have one person online and one person. And I think, is Mo going to do the brief out, or I don't know. If she's not here, we could start with the, okay. So, so we'll now hear from the session that met in the boardroom, and the rapporteur for that was Mo Walzak. Please, it says please keep your remarks to 5 minutes, but I think you can utilize the time to the extent you need to, because we only have 2. Yeah. Of course.
Well,
To go- I can go, I mean, like Alan is, I can talk super fast. Okay. All right, so I was trying to follow a very fast-paced conversation and work things into organizational structure that maybe is wrong. So let's just start with this and see where we go. So I have first critical science needs. We critically need to understand how much sea level rise and how fast that sea level will rise, or how fast that sea level rise will occur associated with retreat of Antarctic outlet glaciers and failure of the Antarctic ice sheets. We need to understand interactions between the ocean and Antarctic cryosphere, ranging from sea ice and floating ice shelves to the interior of the ice sheets, to better predict stability of these environments in the periods of the future. We specifically note that grounding zone processes are of critical importance in constraining these processes, because why not say processes a lot? We need to accurately understand with the greatest degree of precision possible air-sea gas exchange in the Southern Ocean. This is essential to understanding one of the largest non-geologic sinks and potential sources of greenhouse gases in the world. As an extension of all these processes combined, we need to understand how changes in global climate and ice sheet stability will feed back into changes in circulation in the Southern Ocean, which in turn impacts global heat budget and CO2 budgets. Last but not least, we need to document and understand the Antarctic and Southern Ocean biosphere, which is among the most productive on Earth, and we believe is changing rapidly due to increasing fishing pressure, tourism, and climate change. We note developing an understanding of these deeply interconnected dynamic systems, critical to our economic and national security, requires coordination and collaboration between the oceanographic and geologic glaciologic community. Without the comprehensive access to the Southern Ocean, Antarctic continent, and its underlying sedimentary records to be supported by this vessel, we are ceding critical societally relevant global scientific leadership. We note that Norway, Australia, the UK, South Africa, China, Italy, India, France, and Korea, among others, have Antarctic research vessel platforms that exceed current American capabilities. So with regards to critical ship-based infrastructure, the development and support of AUV and ARVs are considered critical for Antarctic research needs across the board. But we also need to be thinking about potential use of the vessel over its entire lifetime and ability to serve future needs with long-term and year-round monitoring. The ship should ideally be capable of deploying and servicing such as would be served by semi-permanent infrastructure, for example, moorings, cabled arrays, acoustic networks, and other types of instruments yet to be determined, capable of capturing a variety of processes over a full annual cycle. We also need the ability to support divers, including a decompression chamber. We need access to the seafloor. Understanding the paleo-environmental record of ocean temperature, circulation, productivity, sea ice cover, and ice sheet retreat is a critical component of understanding processes that occur beyond the observational scale and constraining dynamics in warming worlds where ice sheets have destabilized in the past. This will require infrastructure to support long sediment core collection as well as deep sea drilling. We reviewed the capabilities from different sessions and discussed recurring cross-session themes of a need for ice shelf, shore, and archipelago access, but also shallow water down to around 50-meter access when sea ice conditions will allow. Emphasis on the point that without the ability to use this vessel to some extent as a mothership, we will be disenfranchising a significant portion of the scientific community and the important science they do.
Emphatic importance is on a highly capable workboat, but we also have need for a helicopter as there is really no other way to access ice shelves. Fast flowing and grounded ice is dangerous for fixed wing craft. We need to be able to access ice camps over 20 kilometers from shore for geodetic and geological sampling, and areas armored by heavy over 1.5 meter sea ice. We note that undersubscription of helicopter capabilities is likely a result of institutional dysfunction. This would be addressed if there were interdisciplinary calls for helicopter access. Finally, a lack of helicopter capability is a safety issue in the most remote field environment on Earth. There is attention to the need to scale the operational budget to maximize the capabilities of the ship. But as part of this, what are the costs of not developing infrastructure to service shore and ice shelf-based science and limiting that access to just McMurdo and Palmer? The same core programs will ultimately have to cover the complex logistics and extensive costs of reaching remote parts of the Antarctic margin and continent from these two stations via helicopter or other methods if the science needs to be done, which we all believe it does. We would submit that for the vessel to be maximally efficient in service of U.S. science interests and our funding agencies, we don't just need the ability to land a helicopter, we need the ability for sustained support. We recognize this would involve mobilization costs and fuel. Are there other considerations that we are failing to understand with regards to why the design cannot include shore-based access? We would appreciate a dialogue with NSF on this point and feel we can provide robust scientific justification for this capability in support of a request for congressional appropriation adequate for meeting the actual needs of the U.S. Antarctic scientific community. Could interagency partners be identified to help support these costs? And if additional funding is flatly impossible, what would we have to sacrifice to get this capability? And are those sacrifices acceptable? Finally, we have non-ship-based but still critical infrastructure for Antarctic research. Other important community needs include upgrading experimental facilities at McMurdo and Palmer. We also need ongoing continuous support for modeling and engineering. We need those and those need to be supported at a community-wide or facility basis as opposed to being sporadically supported through individual projects. This directly ties to the need for improved sustained cyber infrastructure for data management to facilitate biological and ecosystem data integration. Data management architecture of GoShip and R2R could be a good model for this. That's all I got.
And just so for the official record, the things that were happening very quickly at the end was a discussion of how operational considerations need to be a part of this, as well as the importance of balancing not just scientific leadership, which a lot of this is focused on, but also basically economic interests and autonomy, as well as national defense. And so those all combine in terms of the appropriateness of assuming that international collaborators are the solution for all of our needed extensions of the logistics of this vessel. So it's a great opportunity to do that. The other things that came up were the opportunities. So it was mentioned a bit about specific calls for helicopter based basically cruises that would include specifically that capability versus requiring folks to propose for an entire cruise. So this might be a way to maximize that investment. And then an additional thought was basically in using that both as a science platform, but also to increase the range of the vehicle or the vessel itself. So there was a few other points that were made at the very end and wanted to make sure that we caught those. Is there anything else? Yeah.
I'm going to put in EG, NOAA, or NASA.
Yeah, sorry. The point was that NOAA and NASA would be necessarily supportive of such an endeavor, but it's most likely the responsibility of NSF in going into that Antarctic support budget.
I will email these notes to all the rapporteurs from the session, and we can have a crack through them and then send them over.
That sounds good. Thank you, guys. That's great. Just on that last point, we had just started in that session getting into the interagency international collaboration and support. And I think Allison mentioned there's now a high-level working group between NASA and NSF about improving collaboration in many areas. And I will say, from my past experience, having multiple agencies come to a budget discussion hearing or something like that and agreeing that something for one agency is a priority and it's important for the US in general is a very powerful thing to happen. Okay. So even if there weren't to be any financial support, having unilateral support for investment in one agency for a capability that's national is actually extremely important. So thank you. That was a wonderful report back. I think we're going to hear from our other rapporteur online, Doug Weens.
Hello. So we had a spirited online discussion, and we didn't discuss so much the science needs, but more how, well, we didn't discuss the science itself, but we did discuss how the science needs went across many of the different groups. So almost all the groups talked about access to land and sea ice, preferably in many cases with a helicopter. People noted that, there's some comment about how infrequently helicopters have been used, but that is because of the way that they're managed, and they've been requested many times and not been available. People noted that helicopters are permanently located on other ships like the Polarstern. And they also noted that there's sort of different ways of operating different ships. And the question is, how will the ARV be operated, 15 to 20 years from now? Will it be the PI, the single PI model that we usually use in the US, or is it like a collection of groups like some other countries use? These are all sort of things to consider. But in terms of the access question, people noted that many areas, like especially East Antarctica, coastal regions, or grounding lines where there's a lot of crevasses and so forth, can really only be reached by sea. And so the ship needs to have a capability to help us reach these areas. Otherwise, we can't reach them at all. The feeling of the group was that the needs for access hadn't really been adequately considered so far. There really needs to be a study that, that would show the trade-offs of maybe incorporating different sizes of helicopters possibly on the ship, and how that would trade off with other capabilities. Like things like, do we really need 55 berths and so forth? If it means giving up access to large parts of the Earth. So that was a pretty extensive discussion. We also talked about drones, and that's a really exciting thing that will develop considerably over the next 15 years. They're currently not, people pointed out, they're currently not useful really due to the regulations, very tightly regulated their uses. And they're also technically not capable enough to do a lot of the work that we would want to do, say, out of helicopters or fixed wing aircraft. But they'll probably evolve substantially over the 10 to 15 years before the ARV becomes operational. And so there needs to be a lot of design flexibility built into the ARV to accommodate where the drones evolve in the next 10 to 15 years, so that that we're not kind of locked into some idea of how the drones are going to operate, which might be obsolete by 10 to 15 years from now. Another thing that we talked about was the need for crustal scale seismic imaging. And it was unclear to us from looking through the documents we were given whether there was capabilities for that, such as built-in compressors, a capability for large streamers on the ship. And, so that's something that probably needs to be evaluated, whether, those capabilities would be available given the current design. And finally, it was mentioned that a really important capability that we sometimes don't think about right away is communication capability, the ability to send large volumes of data back from the ship in real time is really an essential thing.
All right, thank you so much. That was great, and I loved slightly different perspectives than the other group, which is really super helpful. Questions, last minute thoughts by anybody? Everybody's ready for a beer. I don't blame you. All right, well, that marks the end of our workshop. Thank you, everybody. Thank you to the committee, and have a very safe trip home, everyone. Thank you.